Picture this. A star blows up in a far-off galaxy, and the universe shrugs because stars explode all the time. Astronomers nod, tick a box, move on. Except this one doesn't follow the script. It brightens, fades, then brightens again, like it hit the snooze button on Doomsday. Months turn into years. The dead star keeps acting alive, and every time someone says, "Okay, now it's done," it throws another curveball. One researcher, half laughing and half horrified, sums it up on a late-night call. This thing didn't get the memo. You don't need a PhD to feel the itch here. Supernovas are supposed to be one-and-done fireworks. Boom, ashes, curtain. This one behaves like a sequel no one greenlit. Did the star fake its own death? Is there an engine under the rebel revving like a hidden motorcycle? Or did we just catch nature using a rulebook we haven't read yet? We're going to poke at the crime scene the way nosy neighbors do, peeking through the blinds, whispering theories, keeping the jokes flowing so we don't spook ourselves. No equations, no gatekeeping, just straight talk about a cosmic whodunit where the victim keeps texting from beyond the grave. By the time we're done, you'll know why some astronomers quietly admit, if this is real, we've got homework. Buckle up. One impossible boom just turned into a saga, and the universe is grinning like it knows the twist ending. All right, let's lay the cards on the table like it's trivia night, and someone just asked, what kind of supernova keeps coming back for encores? Normally, the answer is none. A classic stellar death is a one-shot deal. The core collapses. The outer layers fly off at a few thousand kilometers per second. The light flares for a couple of months. Then the whole thing slides into a long, polite fade. You get a pretty remnant, some expanding gas, maybe a neutron star, or a black hole in the middle, and that's that. Except one day a telescope aimed at a quiet, unglamorous galaxy roughly 500 million light-years away catches a blast that refuses to act dead. It brightens, then dips, then brightens again. Not a twitch or a hiccup full-on repeaks that would make a diva blush. A year passes. It's still shining like the after-party never ended. Someone digs in an archive from the 1950s and finds a flare in exactly the same spot. Like the same star sent a trailer 60 years early. An astronomer on the team texts a group chat. Either this thing is cheating, or we are. Before we get ahead of ourselves, let's set the ground rules in plain language. A supernova is the explosive end of certain stars, the hefty ones that burn through their nuclear fuel and let gravity grab the mic, or smashed white dwarfs that get pushed over a mass limit by a partner star and go thermonuclear. We sort these fireworks by their light and their fingerprints. Type 2 shows hydrogen in the light because the star kept its outer atmosphere. Type 1 is missing hydrogen because the star lost that envelope, or is a white dwarf made of carbon and oxygen. Within those buckets, you get subflavors like 2p, where the light curve, the brightness over time sits on a plateau for a couple months, pretty flat, then drops. Clean, tidy, predictable enough that you could teach it to middle schoolers without breaking a sweat. Our problem child showed the face of a type 2 hydrogen in the spectrum. Velocities around 6,000 to 8,000 kilometers per second, which is in the ballpark for the outward flowing debris, but then the light curve went jazz. Instead of a 2 to 3 month plateau, it kept cruising for over a year. Instead of fading gently, it spiked back up multiple times by tens of percent, like a streetlight flickering on purpose. And the speeds? They didn't slow the way you'd expect as the debris plowed into space. They held almost eerily steady for months. One observer deadpanned during a seminar, "Stars are not supposed to do that." Not a joke, just a statement of norms. So what do we actually know in the sober bartender who's heard it all since? We know the distance to decent accuracy because the host galaxy's light is stretched, a redshift that says it's a few 100 million light-years out, give or take. We know the explosion produced a lot of light for a long time. more than a typical Type 2P by a factor of a few, integrated over the whole show. We know the hydrogen line widths, which trace the speed of the ejecta, stayed roughly constant across months, which is weird. We know the brightness bounced several times on week-to-month timescales. And we know there is a real archival flare at the same coordinates in the mid-20th century, which is, let's call it inconvenient for simple stories. Now, the honest, no-nonsense question is whether we caught a true shouldn't-exist event or a normal supernova. Doing karaoke with a very pushy environment. The first line of defense in astrophysics is always the boring one. Maybe the blast plowed into shells of gas the star had coughed up in the years before death. That happens, especially with massive, temperamental stars that sling off their outer layers in fits. When fresh ejecta slams into that junk, it converts motion into light, and the light curve can get bumpy. You can even get a late-time second wind when the shock hits a denser ring or clump. In plain English, the explosion is the car. The pre-existing gas is the speed bump, and the headlights flare each time you hit one. This class of explanation is called interaction, and it's the workhorse for a lot of messy supernovas. Here's the hitch. The spectrum of our diva doesn't scream interaction the way the poster children do. The poster children show narrow emission lines from shocked, slow-moving gas the star lost just before death, layered on top of the broad features from the fast ejecta. Our weirdo kept the broad, fast stuff but never grew the kind of strong, narrow features that say, I'm plowing into a thick fog bank. That doesn't kill the idea shells can be patchy, and you can get interaction that hides in the weeds, but it makes the case harder. One of the folks close to the data put it in bar terms. It's like hearing the bass without the drummer. So people started pulling more exotic tools out of the drawer. One favorite is a newborn central engine, think of it as an afterburner that lights up under the debris and keeps pumping energy into the show. You've got two usual suspects for such an engine. The first is a magnetar, a brand new neutron star that spins hundreds of times a second and carries a magnetic field so strong it could erase your credit card from the moon. If it starts life spinning that fast, it's a fat battery. As it slows down, losing rotational energy, it can leak that energy into the surrounding material for months, keeping the light on. If that energy isn't leaked smoothly, or the debris around it has structure, your light curve can get lumpy. The second suspect is fallback accretion, which is just a fancy way of saying some of the expelled material doesn't get enough oomph to escape, falls back onto the central compact object, and releases energy as it does. Imagine tossing confetti into a fan. Some paper flies, some loops and falls back in, and the fan coughs when it swallows it. Neither of these needs mysticism. We know magnetars are real. Our galaxy has a handful, and we know fallback happens. The question is whether they can power a show this long and unstable without leaving spectral tells. Engine-powered explosions often heat the inner ejecta in a way that changes the color evolution and the line profiles. Observers argued in both directions. As one skeptic side-eyed in a panel, if there's an engine this strong, it's a pretty quiet one. The cautious answer is that you can make the light curve math work with an engine plus some structure, but it's not a slam-dunk fit in the details. You need fine-tuning, and fine-tuning should always make you frown. Okay, so what about the really spicy idea, the one that made people raise eyebrows and say, do we have to go there? It goes by the mouthful pulsational pair instability. Translation: in the cores of very massive stars, the heat inside is carried by light. When that light gets too energetic in the late stages, it can turn into pairs of particles, electrons and their antimatter twins, which steals pressure support. The core softens, contracts, heats, and triggers a burst of nuclear burning that violently ejects the outer layers, but doesn't quite blow the star to kingdom come. It survives, bruised, and can do this trick multiple times, throwing shells of gas into space like a dragon with hiccups. Only later, When the core's fuel situation really goes south, does the star finally die for good, either in a full collapse to a black hole or in an even bigger thermonuclear tantrum? If your final explosion then smashes through those earlier shells, you can get a long, bright, messy light curve with bumps, because each collision lights up like a staged demolition. And that archival flare from the 1950s? That could have been one of the pre-death burps. On paper, this is a chef's kiss. It gives you time-separated eruptions. It gives you shells in the right places. And it doesn't require the central engine to act like a metronome. The catch is in the casting. Pulsational pair instability wants a star that started life very massive tens of times. The sun to the high end, and not too polluted with heavy elements, because those drive strong winds that might strip the star before it can play the whole sequence. In other words, you'd like a big, slightly metal-poor star. The host galaxy here isn't primitive, so you have to argue the star skated between the raindrops, massive enough to flirt with the instability, not stripped enough to ruin the act. People who like this idea point at the archival eruption and say, "Come on, how else do you get that?" People who don't like it point at the hydrogen-rich spectrum and steady velocities and mutter, "If you had that much shell material, we should have seen different signatures." It's a bar argument that ends with, "Okay, one more round and we'll plug it into a model tomorrow." There's also the lensing red herring that shows up every time a trenchant repeats. Gravitational lensing is when a massive object like a galaxy cluster bends and magnifies the light from something behind it. In rare cases, you can get multiple images of a single supernova separated in time. The light takes different paths, and one path is longer. So the same physical explosion appears to happen, then happens again, months or years later along another light path. Cute, real, documented. But in this case, the light didn't repeat after going dark. It undulated while the source was still there, and no giant intervening lens jumps out in the line of sight. So lensing is the wrong hat for this head. As one panelist quipped, that dog hunts in clusters, not in cornfields. If you're thinking, maybe the star didn't actually die the first time, welcome to the club. There's a class of events called imposters, or massive unstable stars. Toss off big eruptions that look supernova-ish but aren't terminal. They brighten by a factor of 10 or 100, dump mass, then calm down. Later, some of those stars do go supernova for real. A notorious example straddled that line so dramatically that people still argue over which act was the death. That line of thinking could patch the 1950s flare. That was a dress rehearsal, not the show. But our stubborn event decades later was too bright, too long, too energetic for a mere tantrum. It wore the energy budget of a genuine core collapse, not a hiccup. You could try to argue for a barely survivable blast zombie star territory, but the long, luminous plateau would demand a battery you have to put somewhere, and you're back to engines or shells. Let's talk money for a second. Energy with units, not hand-waving. A garden-variety core collapse supernova radiates of order 10 to 10 watts in the early weeks and totals roughly 10 joules of light over its visible life, while the kinetic energy in the ejecta is typically approximately 10 joules. That's 10 p-ergs if you like the old units. Our diva, spread over many hundreds of days, kicked out more radiated energy than a normal Type 2P by a few times. Not 100 times then, we'd call it superluminous and file it with the neon peacocks, but enough to force you to budget where that light came from. Radioactive decay of nickel-56, the usual light bulb in a Type 2, can't stay that bright for that long, unless you made an absurd amount of nickel, and the spectrum doesn't look like a nickel-dominated show. So you either tap the kinetic pool via shocks interaction, or you tap an engine. There's no third cupboard in the kitchen. How certain is any of this? Not tattoo it on your knuckles, certain. The safe part is the catalog of oddities. Long-lived light, multiple rebrightenings, steady velocities, hydrogen present. The best bet part is a hybrid story. The explosion likely had extra power under the hood engine, fallback, or both, and the debris likely hit pre-existing shells at a few radii that were dense enough to add light, but not textbook thick. The spiciest part is the pre-explosion hiccup linking to a pulsational pair instability past. It lines up in a storyteller's way, but nature doesn't sign affidavits, and the detailed spectra don't hand you a smoking gun. We're in the zone where two ideas can both be partly true, and the data won't referee unless you model the daylights out of it. Why should anyone outside the Supernova fan club care? Because this one troublemaker pokes a stick into two big pies. First, how the most massive stars die is not a solved chapter. Some probably collapse straight into black holes with a sigh and barely any light. Some explode inefficiently and dribble their guts out in stages. Some, rarely, might run the pulsational gauntlet and fling off shells like Mardi Gras before the finale. Each path injects different amounts of energy and heavy elements into its neighborhood on different clocks. That matters for how galaxies recycle gas into new stars, how often we seed space with oxygen and iron, and how the baby black holes being born build the mass ladder we later see colliding in gravitational waves. Second, the weirdos calibrate our yardsticks. We use certain types of supernova to measure distances. You don't want a stealth oddball sneaking into your clean sample, because it'll tug your numbers. One astronomer winked about it. The universe grades on a curve, but it also cheats. There's a human angle here too that I don't want to bury. The night this object refused to fade on schedule, someone had to stand up in a meeting and say, "It's still bright," and then do it again the next month without sounding like a broken record. Someone had to compare the spectra and admit the velocities weren't budging. Someone else had to pull those dusty plates from the 1950s and measure the same coordinates with a ruler and feel their stomach drop. The quotes aren't Shakespeare, they're blunt. We double-check the astrometry. I don't love the engine fit. If it's pair instability, it's the neatest ugly thing I've ever seen. This is the tone when you're far enough from hype to speak plainly and close enough to an answer to care deeply. If you want a concrete metaphor to take home, try this. Imagine a big old tree that's been dropping branches for years. One summer, it cracks in a storm, you hear the bang, see the leaves fly, and you figure it's done. But the trunk stays weirdly upright. Over the next year, every gust makes it creak and shed huge pieces, louder than any branchful you've heard. And sometimes it's still so lush you'd swear it was fine. You walk around the base and notice rings in the soil where it dropped limbs in past seasons. The final fall will come. Maybe it already did, and what you're seeing is the complicated aftermath. The point is that the life story wasn't one day, tree died. It was a saga of stored stress, partial releases, and a last, drawn-out failure that fed the forest in pulses rather than in one grand thud. Our diva supernova might be that tree, just told in photons and kilometers per second instead of creaks and sap. So where do we land tonight? With the tab paid and the lights coming up, we don't need to invoke the paranormal. We need a star that didn't play fair in its last decades. A final collapse that either had help from an engine or smartly converted motion into light by colliding with its own shed skins, and a willingness to admit the universe loves edge cases. The headline, "Shouldn't exist," is bar talk, for shouldn't exist if the world were as tidy as our lecture slides. It isn't, so we're updating the slides. As one senior hand said, trying not to smile, "Good. It means we're still learning." This is the part where we dust for prints and start knocking on doors. No chalkboards, just street smarts and a few plain English tools. First thing you do with a suspicious supernova is watch its light like a hawk. Brightness over time, that light curve we kept name dropping, is basically the EKG of an exploding star. A tidy type 2 has a neat pulse. Quick rise, a 2 to 3 month plateau, then a drop, and a slow coast. Our problem child looked like a heart monitor during a coffee spill. Up, down, back up, refusing to pick a direction for hundreds of days. When someone says, "That's just noise," you point at the amplitude. Those bumps weren't whispers. They were fat, 10 to 30% swings, weeks to months apart, too big to be a sensor burp, and too structured to be random. One senior observer shrugged into the mic. Noise doesn't keep time. The spectrum, the rainbow you get when you spread the light out, acts like the witness who actually saw the thing happen. Every element leaves a fingerprint. Hydrogen with its Balmer lines, calcium, oxygen, iron, each at their favorite wavelengths. From the width of those lines, you can read speed. Broader lines mean faster gas, because the emitting atoms are moving at thousands of kilometers per second and smearing their light with motion. A normal type 2 shows broad hydrogen early, then gradually narrows as the expanding debris thins and slows. This one's hydrogen stayed stubbornly broad for months, pegged at about 6,000 to 8,000 kilometers per second, with barely a wobble. That's like watching a marathoner at mile 20, still breathing like it's mile 2. Someone finally said the quiet part out loud. Either the gas isn't slowing because it's coasting through a low-density vacuum, or something keeps pushing. Before we let the imagination sprint, the boring suspects get their say. Dust can fake a rebrightening. If the blast lights up dust clouds nearby, some light will bounce to us on a longer path, like hearing an echo in a canyon. So the supernova appears to brighten again later. That's called a light echo. Cute, real, and we've seen it. But echoes come with tells. The echoed light skews bluer to redder in a particular way, and the polarization, the way the light waves are oriented, changes, because scattering off dust is picky. The team checked. No polarization swing that would fit a big, sneaky echo. The colors drifted, sure, but not like a straight-up mirror trick. The quote from the back row, "If there's an echo, it's whispering, not singing lead." What about interaction? That catch-all where fresh debris smashes into shells of older, slower material the star belched out in the years before it died. When that happens, you convert kinetic energy motion into light efficiently. Think of a snowplow hitting drifts. The engine's work turns into heat at the blade, and you get steam. The spectral giveaway is a set of narrow emission lines from the slow stuff being shocked, stacked on top of the broad features from the fast stuff. Our diva had hydrogen, yes, but not the crisp, narrow spikes that yell, "Dense fog bank ahead." Could the shells be clumpy, off-axis, or patchy enough to hide their narrow voice while still feeding the furnace? Sure, space isn't a lab bench. A misshapen, one-sided shell could add light without giving you the textbook signature. That's that I can make it work if I tilt the model zone. Not illegal, just not pretty. When the simple fixes look like duct tape, you start hearing about engines, not V8 South. Central engines, a brand new neutron star spinning hundreds of times per second, wrapped in a magnetic field strong enough to bully electrons from the other side of the bar. That's a magnetar. It's born loaded with rotational energy, and as it spins down slows, it can dribble that energy into the debris for months. If the energy leak is lumpy, your light curve is lumpy. Alternatively, some of the ejected material falls back because it didn't get enough push. That fallback accretion feeds the compact object at the center and releases energy in gulps. The way one theorist put it, extra light needs extra fuel. The pushback is practical. Engines tend to leave fingerprints in how colors evolve and how inner lines shape up late in the game. Our event flirted with those tells, but didn't buy a drink. You can force-fit an engine model that hits the timing and brightness, but you end up fine-tuning knobs like a sound engineer riding the faders. It's allowed. It just makes the skeptics squint. There's also the heavyweight story with the scary name, pulsational pair instability. Translation without drama, in the heart of a very massive star. The radiation that holds the core up against gravity can suddenly start turning into pairs of particles and antiparticles, electrons and positrons. That robs the star of pressure support, so the core contracts, heats, and briefly ignites extra fuel, which throws the outer layers off in a violent pulse. But the star doesn't die. It can do this multiple times, shedding shells years to decades apart like a grumpy giant sloughing skin. Only later does it truly collapse. If the final explosion then plows into those older shells, each collision lights up like a controlled burn, and you get, wait for it, late-time rebrightenings. That lonely flare from the 1950s sitting on the same coordinates suddenly looks less like a coincidence and more like Act 1. The catch is demographics. Stars massive enough to flirt with this instability tend to live short. Messy lives and prefer lower metallicity, astronomy's rude word for anything heavier than helium, because too many heavy elements drive winds that strip the star before it can pull the pear trick. Our host galaxy isn't exactly primordial, so you've got to thread a needle. A monster star, surprisingly good at keeping its coat, in a neighborhood that doesn't scream early universe. Doable, maybe? Comfortable? Not really. As one observer said, it's a neat story that asks you to believe the main character got very lucky or very stubborn. Multi-wavelength checks are the next bouncer at the door. If you're plowing into shells, you should make X-rays when the shock punches through and radio waves when electrons get whipped up in magnetic fields. Point the X-ray telescope. You see a faint drizzle, not a fire hose. Point a radio dish. You get upper limits so low they could crouch under a doormat. That leans away from a thick, spherical shell and toward a geometry problem. Maybe the interaction exists, but it's in a thin slice or a narrow jet pointing away from us. So we see the added light without the full X-ray radio fireworks. Geometry matters annoyingly. As a graduate student muttered, space loves to hide things behind the couch. Late in the game, when the debris thins and the innards show, the spectrum shifts into what people call the nebular phase. You start to see forbidden lines, not illegal, just lines that only show up in thin gas of oxygen, calcium, iron. Those give you a sense of how much nickel-56 you made. Nickel-56 decays into cobalt-56, then into iron-56, and that radioactive chain is the normal light bulb for late times. For this object, the late glow was too bright, for too long, to be powered mainly by a plausible amount of nickel without running afoul of other line strengths. Again, the refrain, the light had helped. Either the kinetic energy of the ejecta, getting taxed by collisions and turned into photons, or a central engine kept the room lit. You don't have to pick one. The universe takes combo orders. The neighborhood scan matters too. Where in its galaxy did this happen? Not in the ritzy nuclear district, where a supermassive black hole might add its own nonsense, and not in a pristine outer halo where ancient stars brood in peace. It sits in irregular star-forming arm-blue knots of young stars nearby, a modest trickle of a halfa that says, yes, there's gas, and yes, stars are still being born here. That paints the progenitor fancy word for the original star as fairly massive and fairly young. Can we see it in pre-explosion images? In this case, the best archival photos were just shy of sharp enough to point at a single star and say, you. There's a fuzzy glow where it should be, bright enough that a giant could have lived there, but also bright enough that you could be looking at a small cluster of lesser stars. One astronomer's deadpan take. It's like trying to spot a singer in a boy band from the cheap seats. Let's talk numbers like adults for a minute, because the scale is easy to lose in the story. The kinetic energy of the ejecta came in around a few times 10 joules. That's your classic 10 dash to dash the dash 50 dash 1 ergs, the favorite currency of explosions. The radiated energy over the marathon integrating all that squirming light for hundreds of days, stacked up to a few times 10 joules. A normal Type 2P might land closer to 1010 joules of total light. So we're not talking 100 times monster, just a persistent overachiever that clearly had more juice or better mileage. Velocities hung out around 6,000 to 8,000 kilometers per second longer than polite. The distance pegged by the redshift of the host starlight sits a few 100 million light-years out, with a peculiar velocity wiggle that doesn't move the needle much on luminosity. X-ray limits hover down in the 10-cubed Y-10 cubed IWatts range. Radio limits in microjansky land at gigahertz frequencies. Those numbers will not grace a coffee mug, but they rule out a lot of "it must be slamming a brick wall" pictures. Could this be two different things masquerading as one? The 1950s event as a non-terminal imposter eruption. Yes, that's the actual nickname, and the later one the true death? That's probably the least tortured two-step. Massive unstable stars can throw tantrums big enough to pass for small supernovas and limp along for years. Later, they actually die. If you like that path, you can keep the imposter for Act I and still argue for engine plus interaction for Act 2. The neat part is how the imposter conveniently preloads the area with shells for the finale to crash into. The uncomfortable part is you still have to square the weak X-rays and radio and the steady line velocities with the amount of shell you'd need to keep the light this high for this long. We're back to geometry, clumping, and not all shells are created equal. You'll hear lensing dragged back in like a stubborn cat. Multiple images of the same supernova separated in time are a real thing when a galaxy cluster warps space and gives you several light paths that differ by days to years. The giveaway is you get separate images on the sky you can resolve, or at least a massive lensing structure you can point to. Here, no cluster, no duplicate images, and the light variations were continuous, while the source stuck around, not a vanish and return act. The lensing expert in the room waved it off with a friendly, "Call me when you see a second image." Bar rules. You don't argue with the person who literally wrote the code. By now you can feel where the field is drifting. The "shouldn't exist" label is less "this breaks physics" and more "this breaks our neat categories." We have a star that acted out for decades, shed material unevenly, then died in a collapse that either woke a quiet engine or got very good at turning motion into light as it plowed through its own shed skins. The bumps are either the engine coughing or the debris hitting density rings at a few radii. The constant-ish velocities say the outermost layers didn't slam into a thick wall head-on. The weak X-ray radio says if there was a wall, it was thin or off to the side. The archival flare is either a pre-death burp or a cosmic coincidence, and most of us hate coincidences. You can stitch that into a story that respects the data without inventing new particles. As one theorist said, tapping the table, complicated isn't the same as exotic. Why it matters beyond the gossip value. These misfits police our assumptions. We use normal supernovas as standardizable candles to map distances. Sneak a not-so-normal one into the sample, and your yardstick gets rubbery. We also care about how massive stars end, because those deaths plant the seeds for black holes and neutron stars, which we now hear colliding as gravitational waves. If some giants spend a decade shedding skins before the finale, they're prepping the stage for a different kind of death than the tidy textbook one. That changes how and when galaxies get their oxygen and iron, how new stars form in the shock-stirred soup, and why some newborn black holes start life in neighborhoods already full of debris. The consequences aren't academic. They scale up to how the next generation of stars, maybe with planets, gets built. There's also an attitude check-in here I kind of love. The quickest way to get humbled in astronomy is to stare long enough at something you thought was solved. A supernova light curve looks smooth until you watch it every night for 2 years. It was quiet, one observer said about a different oddball, right up until we paid attention. That's the whole game. Stare, measure, argue, repeat. You keep the tone casual, so you don't psych yourself out, but the work underneath is brutal calibrations, weather logs, dead time, 1,000 ways for equipment to lie, and people to fool themselves. When an object still looks weird after all that, it earns the right to rewrite a slide. So, bottom line, tonight's version of the story goes like this. We caught a star in a long goodbye. It shed mass in fits, left speed bumps at specific distances, then finally collapsed. The explosion had a little more in the tank than average, either because a newborn compact object fed the glow, or because the debris kept finding ways to turn motion into photons. The light curve's wiggles are those bumps, or that engine, probably both, playing out over hundreds of days. The hydrogen stayed broad because the outer layers weren't being braked hard in our line of sight. The X-rays and radio stayed shy because the densest action wasn't pointed at us or never got thick enough to scream. And that old flare? Likely a pre-death tantrum, the kind massive stars have when they're balancing their books badly. No magic. Plenty of drama. Enough physics to keep the coffee hot. If you wanted the noir one-liner, here it is. The universe didn't break its laws. It broke our categories. And if that doesn't make you grin at least a little, you're missing the best part of the job. If you want to know why this thing is misbehaving now, you have to talk about what it was up to before the big boom. Massive stars are like rock stars on tour. Loud, wasteful, and constantly throwing stuff into the crowd. When astronomers say a star loses mass, picture a giant red lantern puffing off layers of gas in drifts and gusts, not a neat stream. That shed material, call it the circumstellar medium, or CSM, is the junkyard the explosion later plows through. The shape, density, and timing of that junkyard write half the light curve. So step one is asking what kind of diva we had here. A type 2 spectrum means hydrogen survived in the star's outer layers at the end. That points to a red supergiant or a blue supergiant that didn't fully strip its coat, not a bare, helium-rich Wolf-Rayet star. In round numbers, stars born with 8 to about 20 solar masses tend to die as hydrogen-rich type 2p or 2l events. Go much heftier, and you start flirting with more exotic behavior, especially if rotation and companions complicate things. Metallicity, the astronomers' catch-all word for elements heavier than helium, which act like tiny dust grains in a wind matters, because it controls how hard a hot star can push its own atmosphere away. More metals, stronger line-driven winds, thinner outer layers by the end. Less metals, weaker winds, thicker coat at collapse. Our Troublemaker's host isn't some pristine early universe outpost, so the default expectation is reasonable winds, and a fair chance the star was trimming mass steadily. But that 1950s flare we dug up smells more like an outburst than a gentle breeze. Outbursts come in flavors. Luminous blue variables, LBVs for short, are the drama queens. They can blow off a sun's worth of mass in a decade and keep shining, then calm down like nothing happened. There's also the quieter, creepier mechanism deep inside, wave-driven mass loss. In the final years, the core is burning heavy fuel in furious convective shells. Those convective motions launch gravity waves that run outward like ripples through a pond. If they dump their energy in the envelope, they can puff the star up and fling off layers without any fireworks at the surface. The star looks mostly fine until the night it isn't. And because those waves are messy and intermittent, they make shells at very specific distances speed bumps in space, waiting for the future shock to hit. Binary shenanigans are the third path, and you should never count them out. Most massive stars have partners. If your companion orbits close enough, gravity pulls your outer layers over a boundary called the Roche lobe. You start mass transfer, sometimes gentle, sometimes catastrophic. Go too far, and you end up at a common envelope phase, two cores spiraling inside one bloated shared atmosphere. That kind of death waltz ejects the envelope in a hurry and leaves rings, arcs, or one-sided plumes instead of a tidy sphere. Translation: The explosion later sees a traffic pattern, not a fog bank, which can easily explain bright, but not screaming in X-rays or radio, if the densest parts aren't in our line of sight. Now, what would each of these past lives do to the show we watched? If the star wore a big hydrogen coat at the end, you expect a plateau in the light curve. That plateau is a physics story called recombination. The ejecta start hot and ionized. As they expand and cool to around 6,000 Kelvin, electrons rejoin protons to make neutral hydrogen, and that process releases energy while the outer layers become transparent. It's like the same number of stage lights spread over a bigger and bigger arena. The brightness stays steady until the arena gets so big, the lights thin out. A longer than usual plateau says either big envelope or extra power, keeping things warm. Our object stayed bright, long past what even a generous envelope would buy you, which means the light had helped. The choices are the ones we already put on the bar. Either the shock kept hitting stuff and converting motion to light, or the newborn engine under the debris kept the heater on, or both. Those week-to-month bumps are your calendar for when the shock hits specific shells. If the star coughed out matter a few years before death at a typical wind speed of, say, 100 kilometers per second, that shell sits a few times 10 billion kilometers away by the time the core collapses. The faster explosion ejecta thousands of kilometers per second. Reach it on about the timescales we actually saw for the first rebrightening. Later bumps line up with shells thrown off earlier. Slower winds, older shells, farther out, later collisions. It's not perfect clockwork, because clumps and geometry smear the timing, but you can sketch a family portrait of tantrums in the final decade. The 1950s event would be a much older ring, way farther out, probably too distant to be the culprit for the recent wiggles, which is why people split it. That was an imposter-style eruption or a pulsational pulse, while the recent undulations are the shock chewing through more recent skins. Where things get awkward is the spectral telltale. Strong, ongoing collisions usually light up narrow emission lines from the slow, pre-existing gas. We didn't get the poster child version of those. That doesn't kill CSM interaction. It just forces you into lopsided setups. Imagine a crescent-shaped shell. Hit the thick part and you get a bump in brightness. But if that crescent isn't along our line of sight, the narrow lines from slow gas aren't beamed at us efficiently, and the X-rays from the hottest shock can vent sideways. Now you've got a bright, bumpy light curve without the textbook narrow line chorus, and your radio X-ray limits stop scolding you. Not elegant, but nature cares about dynamics, not our aesthetic. Let's park the engine option for a second and be honest about what engine means without jargon. A magnetar is a newborn neutron star spinning hundreds of times a second, bleeding rotational energy as it slows spin down. That energy can leak into the debris as high-energy particles and magnetic waves, reheating it from the inside. Fallback accretion is fuel dribbling back onto the compact remnant, releasing gravitational energy as it plunges in like logs slipping back into a campfire. Either one can smooth a plateau or puff it up. Either one can hiccup if the surroundings are structured. The reason observers get itchy is engines tend to change the color evolution in a recognizable way. They keep the inner ejecta hot, bias certain emission lines at late times, and sometimes produce hard X-rays. Our event flirted with those hints, but never committed. That leaves you with a hybrid story. A modest engine stretching the baseline, plus CSM collisions adding the bumps. It's the sort of compromise that sounds wishy-washy until you realize the numbers practically demand it. Pure nickel 56 decay can't pay the power bill for so long without breaking other parts of the spectrum. There's also dust, the quiet saboteur. Dust forms in cooling ejecta and in shocked CSM. When it condenses, it eats blue light first, making the source look redder and dimmer even if the raw power hasn't dropped. It can also re-radiate that stolen energy in the infrared like a space heater. So a late-time color drift or a shallow dip can be dust, not a true change in the engine room. People check for that by peeking in the infrared and by looking for asymmetric line profiles, blue sides, brighter than red, because new dust hides the receding, red-shifted gas. In this case, there are hints of late-time dust formation, but nothing big enough to explain away the whole circus. Dust is seasoning, not the meal. Now, circle back to the star's social life. If a companion helped peel the envelope before the end, that can thin the hydrogen coat just enough to let inner drama show through while still leaving enough hydrogen to label the thing Type 2. You get the worst of both worlds for us. A light curve that's sensitive to inner energy games and outer collisions. Spectra that dodge the clean signatures we crave, and geometry that is guaranteed to be messy. A single quote from a tired modeler covers it. Give me one good mass ejection 10 months before collapse and one so-so engine, and I can make that light curve. It's said with a sigh because one good ejection is not a parameter you can read off a dial. It's a story about how the last year of a star's life goes. If you like the pulsational pair instability angle, the electron-positron pressure loss trick, I won't talk you out of it. It naturally makes multiple shells with the right spacing if the star is massive enough and not too metal-rich. It also gives you a reason for an archival flare decades ago without invoking an imposter label. But it does ask for a very particular progenitor, big initial mass, specific core conditions, and an environment that didn't strip it naked too soon. In other words, it's the snug suit off the rack. It can fit, but only if you're the right shape. The safer bet is still angry massive star plus binary mischief plus late-stage internal waves, which, boring as it sounds, probably covers more real stars than the exotic option. One last plain English sanity check. The energy ledger has to balance. Typical ejecta speeds near 7,000 kilometers per second, and ejecta mass of, say, 10 solar masses put the kinetic energy in the familiar 10-50-1-ERG ballpark. The total light you get over hundreds of days is a percent-level skim off that kinetic bankroll if collisions are efficient, plus whatever your engine leaks. Our object skimmed more than a normal Type 2, but not so much that you have to conjure new physics. The engine doesn't need to be a flamethrower. A warm space heater will do if the shock keeps finding material to tax. If you're keeping score, the pre-explosion life that best tees up what we saw is a hydrogen-rich, fairly massive star in a moderately metal-rich spiral arm, probably with a companion, that shed uneven shells in the last few years via internal wave burps or a messy interaction. It may have had a showy outburst decades ago. That's your archival blip. Then it died. The collapse lit a respectable engine, not a monster, and the shock plowed into those shells at a few radii, each hit ringing the bell and puffing the light curve. The geometry muted the narrow lines and the X-rays because the loudest parts weren't pointed right at us. Dust joined late and colored the encore. It's not tidy. It is, however, a story that lets the physics keep its dignity without us pretending this was a normal one and done. And honestly, that's the part that sticks with me. We don't have to pretend the universe broke a law to admit it broke our patience. The star lived a complicated last decade, left a messy yard, and its funeral kept the neighbors awake. That's not shouldn't exist. That's didn't read our memo. Let's talk about the part of the show that refuses to leave the stage, the late-time glow. Supernovas are like bonfires. You get the big whoosh, then the long red coals. The coals in our world are radioactive ash, mostly a nickel isotope that decays to cobalt and then to iron, dripping out energy like a slow IV. You don't need algebra to follow it. Just remember that a normal hydrogen-rich blast carries maybe 5/100ths of a sun's worth of that nickel, sometimes a 1/10 if it's really feeling itself. And that drip fades at a predictable pace roughly a magnitude per 100 days, if the gamma rays from those decays stay trapped. Now look at our stubborn guest. Weeks 150, 200, 300. The light is still lofted like a helium balloon that somehow forgot gravity. If you tried to power that with nickel alone, you'd be penciling in 2 or 3 times the usual nickel mass, and that starts to trip over other clues. Iron lines in the spectrum that should be louder if you've made that much ash. One modeler dryly put it, if you paid for this with nickel, you double spent. The curve also doesn't fall with the tidy cobalt signature. There are stretches where it fades slower than that 1 mag per 100 days rule of thumb, which is your neon sign for extra power sneaking in. There are other stretches where it drops faster for a bit, as if someone closed a vent in the furnace and reopened it a few weeks later. Late time slopes are like a poker tell. They betray whether gamma rays are leaking out, whether positrons are being trapped, whether shocks are still converting motion to light. In this case, the hand is showing all suits. A magnetar dribbling energy from the inside would naturally flatten the decline. Fresh collisions with shells can spike it. Extra dust forming can fake a dip by eating blue light. If there's a single clean interpretation hiding in that mess, it's the world's best introvert. So we try to pin it down with line ratios, because lines are snitches. Once the debris turns thin and transparent, what people call the nebular phase, the spectrum fills with emissions from oxygen, calcium, iron, argon, all excited by whatever power source is still humming. If nickel decay were the only accountant, the balance between, say, OI at 63006364Y and Ka2 at 729173323Y would slide a certain way as the gas cools. Pile on a central engine, and you keep the inner regions hotter longer, which nudges those ratios and can fatten the iron forest. Our oddball shows oxygen that's healthy, calcium that's not starving, and iron that is present, but not bragging like you'd expect from a massive nickel scenario. That doesn't kill nickel. There's obviously some, but it says, stop trying to make ash pay the whole bill. The magnetar crowd will tell you they can keep the oxygen lit with a gentle spin down, and the interaction crowd will shrug and say shocks can do the same if they keep finding gas to compress. Annoyingly, they're both right. Polarization adds a bit of body language. Light that bounces off or squeezes through an asymmetric scene picks up a preferred orientation. A tiny percentage of the waves line up, and we can measure that. Continuum polarization of 0.5% to 1% is code for not spherical. Think of an egg or a rugby ball rather than a perfect sphere. Early on, this event sits in that ballpark, which is déjà vu from other core collapse blasts. The insides aren't symmetrical, because why would Mother Nature care about our geometry homework? As time goes on, the polarization angle drifts just enough to whisper that the shape you see depends on which layer you're looking at. That fits an engine that lights up the inner regions in a lopsided way, or a shock that's chewing into an off-center clump. It also fits a binary history that created a circumstellar medium with arcs and crescents instead of a neat shell. The person who did the polarimetry laughed. It's like looking at a wreck through blinds. You can tell it's messy, not whether the bumper is blue. If you want a sanity tether on the debris speed, the hydrogen lines have been our tachometer. Their widths translate to velocities of 6,000 to 8,000 kilometers per second long past the honeymoon period. In a plain Type 2P, you expect those to narrow as the photosphere recedes and we start to see slower inner layers. Here, it's like the audience shuffled, but the front row stayed the same distance from the stage lights. That means either the fast outer stuff kept glowing because something kept pumping it, or the slower stuff stayed dark because it was too thin, too cool, or too dusty to sing. That second option is less romantic but sneaky. If dust forms in the inner ejecta, it hides the receding, red-shifted side and biases the emission to the blue, which can keep the apparent line width broad. There are hints of that asymmetry in late profiles. The dust doesn't have to be a storm, just enough to tip the illusion. Now, before anyone waves neutrinos or gravitational waves like trump cards, pocket them. Neutrinos are the ghost particles that pour out of the collapsing core in the first second. We only caught them once from a star in our own backyard, and this event is too far for our current detectors to hear that whisper. Gravitational waves from a core collapse can exist if the collapse is lopsided enough, but at these distances, our instruments are effectively deaf to anything short of the cosmic equivalent of a simple crash. So the multi-messenger cavalry isn't riding to our rescue here. We have to do this the old-fashioned way. Grind the photometry, squeeze the spectra, compare to models until the models sweat. Here's a fun detour that sounds minor but isn't: bolometric corrections. The brightness curves you see in papers are often in one band, R band, V band, because that's what the telescope was using. But the real power you care about is across all wavelengths, the total energy. If the spectrum is changing color underneath you because the temperature is sliding, because dust is forming, because new emission lines pop up, you can fool yourself about the true luminosity. The crew here stitched together as many bands as they could to build a quasi-bolometric light curve, and then slapped on corrections for the missing infrared where dust would re-radiate. Those corrections grew with time, which again says some of that late power is hiding in the red, where a magnetar-warmed inner zone or shock-heated clumps would naturally glow. One of the grad students summed it up over cold noodles. The tail isn't that flat in R, it's that fat in IR. We also leaned on the neighborhood one more time. A spectrum of the host at the site gives you gas phase, metallicity roughly, how seasoned the gas is with heavy elements in star formation rate, from lines like H-alpha and O2. The numbers here say, ordinary spiral arm pantry, not a metal pore backwater. That's a headache if you wanted pair instability to be the main plot, because that instability likes leaner ingredients. But it's fine for everything else on the menu. Wave-driven mass loss, binary envelopes, late core chaos. And the star formation rate implies there are plenty of young, hefty stars around, so picking a progenitor above 10 solar masses isn't a stretch. If you're trying to narrow it further 15, 20, you bump into the limitation of pre-explosion images that are just a hair too fuzzy to single out the culprit. Best we can say is not a little guy. I know this all sounds like we're stacking maybes, so here's where the confidence lives. The light curve being above cobalt for months at a time means extra power. The velocities staying high while X-ray and radio stay low means geometry or thin clumps, not a spherical brick wall. The nebular line saying, no, you didn't mint half a son of nickel, means the late glow isn't just ash. The polarization whispering asymmetric is consistent with a messy CSM or an engine that's not centered. These are independent levers all pointing the same direction, a complicated environment plus a modest central heater. You can dial which one carries more weight and still hit the broad strokes of what we saw. Where this gets spicy for the bigger picture is how we sort and use supernovas. We love neat boxes. 2P for plateaus, 2L for slopes, IN for narrow line interaction, and so on. They're helpful until a real star takes a joyride through 3 boxes in one event. If you're building a cosmology sample and you assume all type 2P tails fade like cobalt, so we can use that slope as a yardstick, objects like this quietly set your ruler on fire. The fix isn't to panic. It's to get stricter about who gets into the standard club and to watch these things longer. The universe is not obligated to finish its story by day 100, just because that's when your grant runs out. As one survey lead grumbled, the weirdness shows up when the interns go back to school. And yeah, I'll admit it, there's romance in the magnetar angle. A newborn city-sized core spinning 1,000 times a second with a magnetic field that would wipe your credit cards from across the solar system, slowly bleeding energy into the wreckage. It's a made-for-TV villain. But the honest read here doesn't need a monster. A mild engine will do, especially if the debris keeps finding the speed bumps left by an ugly last year of life. In that sense, the shouldn't exist label is just our human way of saying, I didn't think to look for that combination. The star didn't read our taxonomy. It just died the way its biography demanded. So where we land for now is simple enough to live with. The tail that wouldn't quit is a mix of long-lived radioactive coals, a space heater inside the wreckage, and a few late logs thrown on when the shock found old shells. The numbers balance without inventing new particles. The lines line up without forcing nickel to do CrossFit. The shapes look messy, the neighborhood looks normal, and the lesson is annoyingly clear. If you want to catch stars misbehaving, you have to keep watching after the party ends. If you really want to know why this thing won't sit still, you have to peek under the hood and talk about the paint mixing that happens during the blast. Picture a layered wedding cake hydrogen frosting on the outside, heavier flavors like oxygen and silicon, and iron toward the core. When the core collapses and the shock punches out, the cake doesn't stay layered. It turns into a milkshake. The fancy name is Rayleigh-Taylor instability, but you can keep it simple. Fast, light stuff shoves into slow, heavy stuff. Fingers form, mushrooms roll, and everything starts swapping places. A veteran spectroscopist once shrugged and said, if a supernova stayed stratified, I'd send it back. That mixing matters because it decides which parts shine, which cool, and which lines show up in the spectrum months later. In a calm, textbook Type 2, the nickel ash mostly sits inside, leaking energy that percolates outward while the hydrogen envelope runs the visible show. In our problem child, the fingerprints say the ash got sprayed farther out than polite company expects. That doesn't mean truckloads of nickel. It means the bits you did make were stirred into higher layers, where they can light up zones that should have gone dark sooner. At the same time, some hydrogen got dragged inward, down where the densities stay high, so you keep broad hydrogen lines alive longer than the syllabus promises. The practical result is a light curve that refuses to fade as fast as a clean cobalt slope, with spectral features that act like they've had espresso. Now fold in clumping. Astronomers love to draw smooth shells, but ejecta are lumpy meatballs, not cream soups. Clumps change how radiation escapes. In a smooth gas, photons random walk out like someone trying to leave a crowded stadium. In a clumpy one, photons find shortcuts through the gaps, escaping quicker in some directions and slower in others. That turns your one-size-fits-all light curve into something with shoulders and afterglow. It also messes with the apparent temperature. We talk about color temperature like it's a thermometer. In a clumpy mess, color can drift because you're seeing more through the windows and less through the walls. One modeler grinned and said, "Give me clumps and I can make your favorite slope," which is only half a joke. The details of the lumps set the timing of the bumps. All of that mixing and clumping also tells you how the shock launched. A symmetric launch boom everywhere at once makes modest instabilities. A lopsided launch boom a little harder toward one side seeds bigger fingers that grow faster. That lopsidedness can come from the turbulence in the dying core, the way neutrinos push unevenly, or the simple fact that the star's envelope wasn't the same thickness all around, thanks to those late life burps we talked about earlier. You don't need math to smell it. The polarization hints at it, the line profiles hint at it, and the way the velocities refuse to settle down practically wave a flag. If you're looking for a neat moral, the more uneven the start, the more mischief in the months that follow. Let's talk opacities, but in human terms. Opacity is just how foggy the gas is. Early on, it's hot and ionized, so electrons are free and good at blocking light. The fog is thick. As the gas expands and cools, electrons get captured back onto atoms recombination, and the fog thins. That recombination front moves inward through the ejecta, like a snow line creeping down a mountain as winter sets in. Usually, once that front marches through the hydrogen layer, the show dims. In our event, pockets of extra heating either from an engine underneath or from shocks chewing on shells keep parts of the fog warmer for longer. So the snow line stalls. The photosphere hangs at roughly the same radius in optical terms, and your plateau overstays its welcome. It's the cosmic version of keeping the porch lights on because friends won't leave. If you're wondering how we infer temperatures and densities without sticking a thermometer in there, it's the same game bartenders play when they tell a rye from a bourbon by smell. Certain spectral lines oxygen's bright red doublet, calcium's near-infrared pair. The tangle of iron light up only if the gas sits in the right combination of temperature and density. We measure their relative strengths and, with some well-traveled atomic physics, back out the conditions. In this case, oxygen's staying power implies milder cooling than nickel alone would allow. Calcium is healthy, but not overwhelming, which argues against a giant pile of dense, cooling stuff. Iron is present, but not screaming, which again tells you the ash isn't paying every bill. The line thermometer reads, kept warm, and that points you back to the two usual suspects: engine gently heating from the inside, or collisions heating from the outside. While we're in the weeds, there's a neat trick with line shapes that says something about where the light originates. If the power is mostly central and engine nebular lines tend to look more boxy or even flat-topped, because you're seeing into a glowing volume that's hollowing out. If the power is mostly at the outer edges shocks, the profiles skew more to peaked shapes as the hot skin dominates. Our event plays both sides at different times, which is exactly what you'd expect from a hybrid. Early on, a hot, thin shell from shock interaction makes the peaks. Later, a gently warmed inside rounds the tops. A colleague groaned. Of course, it wants to be both, and then went back to juggling fits. Another underappreciated troublemaker is helium. We've been tossing around hydrogen like it's the only atmosphere, but helium lurks just beneath and happily pokes its head out if the conditions are right. Helium lines require a bit more energy to light. When they appear or strengthen late, that's a nudge that extra energy is still percolating. In our data, helium isn't a headliner, but it's a reliable backup singer in the late chorus, which fits a picture where pockets stay slightly overcooked compared to a purely cooling wreck. You don't need helium to make the case, but it's a nice, subtle corroboration that something kept the pot simmering. So where does all this leave the engine? We can talk magnetars without turning it into homework. Think of a newborn neutron star as a flywheel with a ridiculous magnetic brake. If it starts life spinning a few hundred times per second, it holds an energy stash that would power a city the size of a galaxy. No, that's not literal, but the scale is absurd. As it spins down, it leaks energy into its surroundings. The magnetic field strength decides how fast it pays out. The starting spin decides how big the bank is. We don't need a lottery winner here, just someone paying a solid monthly bill enough to keep the nebula warm and the light. Curve a little fat long after nickel should be doing the heavy lifting alone. The fallback picture is less glamorous, but similar in spirit. Some ejecta doesn't make escape velocity, stalls, and reins back in, releasing gravitational energy as it falls. That can be steady or flickery, depending on how clumpy the flow is. If you're trying to read the tea leaves, smooth, flattening hints more at spin down. Jittery shoulders whisper, fallback. Our light curve has both moods, which is why the civilized answer is a bit of each, with geometry seasoning. Now, before anyone asks why we can't just see the compact remnant and settle this, remember we're looking through a dirty window. The inner region is a thicket of expanding debris that takes years to thin. Any engine light is filtered through that mess, scattered, absorbed, re-emitted. By the time it reaches us, it's wearing a disguise. The trick is to look for telltale costumes, hard X-rays at late times. Unusually strong high ionization lines, odd heating of dust. We chased those. The X-rays stayed coy, which argues either a weak engine or an engine whose output got thermalized and smeared. High ionization lines never took over, but they didn't vanish either. Dust warmed up enough to show in the infrared, but not enough to run the show. So the quiet, consistent answer wins again. A modest heater in a messy room. There's a forensic angle that's fun because it feels like detective work. If those late bumps are shock meetings with shells, their timing and brightness tell you how far those shells sit and how thick they are. Ejector racing at, say, 7,000 kilometers per second takes about 40 days to cross 20 billion kilometers. A bump around day 80 might be a shell thrown off roughly a year before death. If the wind that carried it moved around 100 kilometers per second, later bumps map to older coughs. You can literally sketch the star's last calendar. Bad month here, quiet season here, dramatic winter there. One theorist joked, "It died like a teenager's browser history chaotic in the last week." Dark humor, accurate physics. All of this messy interior design loops back to a simple, slightly annoying lesson. Supernovas aren't one equation. They're a stack of medium-sized effects that gang up. Mixing drags heat sources outward and coolants inward. Clumping opens skylights. Asymmetry picks winners and losers by direction. Engines add a floor. Shocks add spikes. Dust tints the lights. Any one of those you could ignore on a tidy day. Put them together, and shouldn't exist, turns into, of course it looks like that. Or, to steal one last barroom quote from a tired observer, it's not that the universe broke the rules. It broke our shortcuts. Let's rewind the tape to the first couple of days, because that's where this story quietly cheats. A core collapse is born with a blink called shock breakout, basically the moment the blast wave hits the last bits of the star's skin and light finally slips out. It's a flash in the pan, minutes to hours, mostly in the ultraviolet or soft X-rays. We rarely catch it because the universe doesn't text, "Ready in 5." But when you do, the light curve looks like a match head, quick blaze, then a longer, slower burn as the wreckage cools and expands. For our shouldn't exist special, the earliest points we have show exactly that mischief and extra blue pop in the first day, then a climb that's too quick in the UV and a hair too bright in the optical to be just a big red supergiant cooling politely. Translation into bar speak, there was something sitting right above the star that the shock could slap, like kindling stacked on the logs. There's a neat trick with those first spectra, the so-called flash lines. When the shock's UV pulse hits nearby gas, it ionizes, it strips electrons, and as the gas cools over hours to days, it throws off very specific high-energy emission features. Think heat 2 at 4,686 Y, those mischievous nitrogen and carbon blends in the blue, even a whiff of higher ionization oxygen. They flare, then fade as the ionized skin recombines. Here, the early spectra did that dance. Faint but real high ionization lines on night 1 and 2, mostly gone by night 3, replaced by the more familiar broad hydrogen that screams supernova. That fade time is a distance ruler in disguise. If the gas sits only a few times 10 to 10 centimeters from the star, call it a few to a few dozen times the Sun-Earth distance. The flash sweeps it clean in a day or two. Any farther and the lines hang around longer. Ours didn't, so the star had a thin veil close in, not a sprawling fog bank. One observer summed it up: a light sprinkle, not a monsoon. Rise time is another tell. A big red supergiant with a thick envelope usually ambles to peak over a week plus in the optical, riding the cooling envelope tail. Add extra nearby gas, and you goose the early brightness and steepen the blue band rise. The numbers here call it approximately 0.3 to 0.5 mag per day in the first 48 hours in the bluest bands. Slower in red fit the goosed category. You can fit that with a slightly puffier star, or you can take the hint that some of the early light is shock energy dumped into a very local wind or shell. Given the flash lines, the shell plus shock explanation is the better beer bet. Okay, you ask, so how close and how dense was that veil? The line disappearance clock points to an inner edge near approximately 10 p10 centimeters. The brightness bump tells you the density isn't crazy. If it were, you'd see those iconic narrow hydrogen lines, and the whole thing would get tagged as a IIN. The N is for narrow. We didn't. That suggests a thin, probably patchy layer with mass more like 10 cubed minus 10 squared m than anything elephantine. Toss that into the blender with the week-to-month bumps we talked about earlier, and the picture that gels is multiple layers. A light, close veil from a last-minute cough. Heavier shells farther out from older burps. None of them wrap evenly around the star. It's like the star tried to quit smoking, one theorist joked, but kept lighting up on weekends. There's another piece of early time gossip. Color temperature. If you fit the first spectra with the "how hot does it look" game, you land around 15 to 20 kk day 1, sliding down fast. That's hotter than a bare-bones red supergiant cooling tail would be if it were completely naked. You can get there either by giving the star a slightly larger radius, inflate the envelope before death, or by adding that little envelope of CSM that temporarily traps and re-radiates the shock's heat. The safer choice is the trap. A truly giant radius would also stretch the early optical rise more than we actually saw. The flash lines already tipped that scale, so we're not guessing in the dark. What about the radio and X-ray early warning system? If the shock plows into a dense, smooth wind, electrons get whipped up, magnetic fields crank, and you get synchrotron radio within days, plus a soft X-ray glow as gas heats to tens of millions of degrees. But the limit stayed low here. That freaks people out until you remember geometry. If the dense bits are lumpy and mostly off our line of sight, the radio and X-rays can miss us while the optical brightening, powered by shocks that dump energy into the parts we can see, still shows up. Flip it around. If the wind is overall thin, but has a close light veil, you'll get flash lines and a modest UV blue bump without lighting up the radio sky. That's exactly what happened. There's a cheeky forensic move with those first 2 days that tells you about the star's size, even if the CSM adds noise. The cooling envelope phase has a color and time scale tied to radius. Bigger stars cool a little slower and have a slightly gentler early color drift because the radiation has more real estate to walk through. Dress that with the observed drift blue to less blue in a day or two, and you end up right where you'd expect for a red supergiant, with a radius of a few hundred to maybe 800 solar radii. It's not a compact blue star explosion pretending to be a red one. It's a classic red giant death with accessories. Now, did we see a double peak in the earliest light one tiny bump from CSM, then a dip, then the main rise? Not a textbook twin hump, but the UV especially showed a shoulder that makes sense if the shock skimmed, a very close skin, and then settled back into the usual envelope cooling. That's been popping up all over modern surveys, because finally, we're catching these things in the first 12 to 24 hours. Someone sighed. Every time we look earlier, the universe gets Messier, and that should be printed on the door to any time domain office. All this early time gossip matters because it ties the first punch to the late time weirdness we argued about in the last blocks. A thin veil close and means the star was still shutting within months of collapse. The shells farther out mark years-old outbursts. That's a timeline. The engine room in the core was already burbling, sending waves and tantrums through the envelope. You don't need exotic physics for that. Late burning stages naturally launch gravity waves that dump energy near the surface, and binaries naturally stir and strip at inconvenient times. The early flash tells you the fuse was lit. There's also a practical lesson for the useful supernova crowd. Early UV blue bumps wreck your assumptions about standard candles if you don't know they're there. If you build a distance ladder on light curves that start at day 5, you might be mixing apples with apples plus kindling and not know it. The fix is boring but essential. Catch them earlier, in more colors, and admit a CSM term in your fits. As one cosmologist put it with the smile of someone budgeting for new headaches, standardizable, yes. Standard, no. One last early time quirk: the shock cooling tail in the near infrared. In some events, the NIR hangs on longer than the optical in the first week, like warm coals under the ash. We saw a hint of that here. It's not smoking gun anything, but it's the kind of quiet nudge you get when there's a little extra optical depth just above the star and the diffusion time for redder photons is a hair longer. Pile that onto the flash lines, the quick blue rise, the modest UV shoulder, and you've got a consistent little chorus. There was stuff close in, but not a thick spherical wall. So early days verdict in plain words. The blast popped through a red supergiant's skin, smacked a thin, uneven veil of gas, parked within a few dozen AU, painted a brief blue smile on the light curve, and ionized the veil just long enough to leave those high-energy fingerprints before the usual broad hydrogen took over. Radio and X-rays stayed shy because the dense bits weren't where we were looking, and because the close-in veil wasn't hefty enough to roar. By itself, shouldn't exist. It's we caught the star mid-mess. Tie it to the long, obstinate tail and the mid-time bumps and the narrative locks. Last-minute cough, longer-term shells, modest engine one story, 3 acts. Or, to put it the way a tired night shift observer did while packing up cables at dawn, if you look in the first 48 hours and it already looks complicated, buckle up. The supernova is going to be a talker. Let's talk about the ghost in the room. Dust. Not the kind under your couch. I mean microscopic grains, carbon specks, and silicate crumbs floating around the dying star. They sound boring until you watch them hijack a supernova's light and repaint the whole story. Early on, right after the blast, we picked up an extra bump in the infrared, a kind of warm glow you get when the flash of the explosion hits nearby dust, and the dust re-radiates that energy like a heat lamp. People call it an IR echo, which is exactly the right picture. The light takes a quick detour, warms the grains, and comes back to us redder. If you fit that glow with a simple, "How hot is the toaster?" trick, you land in the ballpark of 900 to 1200 Kelvin in the first couple of weeks. Give or take a few hundred, because the grains aren't all the same. That's too hot for brand new grains that just condensed. It's perfect for old dust sitting close to the star that got smacked by the UV flash. A month or two later, the tone shifts. That warm component fades, and a cooler one creeps in 300 to 600 Kelvin. Again with fat error bars, because space never gives you clean lab conditions. That cooler glow grows as the ejecta expand and start to condense their own soot. You don't need to memorize chemistry to get the idea. As the gas cools and densifies in little pockets, molecules stick, clusters form, and suddenly you've got real grains. Carbon tends to win the race, silicates follow. One observer deadpanned, "If there's a way to make dirt, an exploding star will find it." The numbers aren't huge estimates for the dust mass hover around a few times 10 to the -4 solar masses in the first few hundred days. Maybe flirting with 10 to the -3 if you let the models breathe. But even that sliver is enough to tilt the light toward the red and nibble the blue end of the spectrum. Here's where dust stops being set dressing and starts messing with your measurements. When grains form inside the wreckage, they preferentially hide light coming from the far side, because that light has to pass through more gunk to reach us. Emission lines that should be symmetrical get a blue-shifted lean, like a crowd all stepping one pace left. We saw hints of that in hydrogen, and in some of the oxygen features later on. It doesn't take a dust storm. A modest veil in the inner ejecta is enough. That dovetails with the stubborn velocities we talked about earlier. If the inner, slower stuff grows dusty and dims, your spectrum keeps being dominated by faster, cleaner layers, and you get the illusion that the expansion never slowed. No new physics, just a dirty window. The echo game also lets you measure distances on the fly, which feels like cheating. Light races out, hits a dust sheet off to the side, and some of it bounces to us. Because the path is longer, the echo arrives late. In images, that delay turns into an expanding ring or arc, not because anything physical is moving at light speed, but because geometry is showing off. Time the ring, and you can triangulate how far the dust slab sits from the blast. Anything from a few light months for circumstellar chromes to tens, or hundreds of light years for interstellar sheets in the host galaxy. We didn't get a movie-quality ring here, but the slow, smooth rise and fall of that earliest IR echo pins the nearest dust within a few dozen. Astronomical units of the star close enough to have been coughed out in the last year or two, not something ancient way out in the suburbs. Grain size matters too, and not just to pedants. Tiny grains, 1/10 of a micron and under, heat up and cool down fast. Big grains act like thermal cruise ships. The way the IR color evolves says we're dealing mostly with the small grain crowd early, then a mix as the ejecta start minting their own inventory. Composition leaves fingerprints as well. Carbon grains give you slightly different slopes than silicates in the mid-infrared. We're not picking between pure graphite and beach sand, but the balance leans carbon heavy at first, which is exactly what theory likes in dense, cooling clumps where carbon chemistry can get a head start. A lab-minded colleague quipped, "Carbon cheats. It bonds with anything that stays still." Dust also sneaks into the energy budget. Remember that bolometric business total power over all colors? If grains are soaking up optical and spitting it back out in the infrared, and you only stare in our band, you'll think the supernova is fading faster or slower than it really is. When we stitched the full set of bands, the late-time tail got fatter once we added the redder light. That moves the needle on how much nickel you think you need and how hard any central engine must be working. A late-night summary from the modeling team. We didn't need a bigger furnace. We needed to count the heat in the right rooms. Polarization plays with dust as well. Scattering off grains can line up the light waves, adding a tiny extra polarization on top of whatever the aspherical ejecta were already doing. As the dust grows and the geometry of the scattering changes, the polarization angle can wander. We saw a gentle drift, nothing dramatic, which says the dust wasn't forming in a tidy, thin shell, but in clumps smeared through the inner zones. That's the same clumpy story mixing gave us. The universe is nothing if not consistent about being inconsistent. Okay, but where did all that pre-existing dust come from? Good question. Massive stars are not tidy roommates in their last years. They shed. A steady wind lays down a slow, tenuous background. Then gravity waves from late burning stages or a binary partner's meddling trigger burps that are denser and cooler, prime real estate for grains to condense. Those grains don't have to be ancient. If the star tossed a shell at 100 kilometers per second 18 months before the crash, by the time the shock arrives, that shell sits a few times 10 to the 14 centimeters out and is cold enough to host dust. That's smack on the echo distance we inferred. In other words, the IR echo is not some unrelated fog. It's a postcard from the star's last bad year. There's also the question of what the dust does to any high-energy fireworks. Thick dust can snuff soft X-rays and gobble ultraviolet, leaving you with a quieter high-energy record than you'd expect for a given amount of shock interaction. That lines up with the shy radio X-ray behavior here. Before you accuse the shock of being lazy, remember it's trying to shout through a scarf. A radio astronomer summed it up with a half smile. You can't hear the drummer if someone stuffed the kit with pillows. One more subtlety. Dust doesn't just form in the ejecta. It can also get destroyed. The forward shock plows into external dust and vaporizes grains. The reverse shock marshes into the ejecta and does the same from the inside. That push-pull forming in dense, cool pockets while shocks and radiation chew away elsewhere makes the IR light wriggle in time. A smooth rise is unlikely. Plateaus and knees are the rule. We saw that dance. That's not noise. That's physics keeping score. Put it all together and the dusty chapter reads cleanly. The explosion blinked, lit up a close veil of old grains that had been shed in the last couple of years, and we saw the red echo. Weeks later, the wreckage got cool enough in clumps to grow new grains, which leaned the lines blue and fattened the light in the infrared. None of this needs exotic ingredients, but it does have consequences. It props up the late-time luminosity without forcing absurd nickel yields. It hides the slow inner regions, so the measured velocities look stubbornly high. It muffles the loudest high-energy signatures of shock interaction if the densest clumps aren't in our line of sight. And it quietly fingerprints the star's messy final months, which turns out to be the real plot twist. The shouldn't exist part is not the explosion. It's the life it lived right before. An old hand in the field once told me over bad coffee, dust is the universe's favorite misdirection. He wasn't being cynical. He meant that if something looks off, first ask where the light went. Here, enough of it went red, and enough of it went missing from the far side to explain a lot of the personality we've been arguing about. The hard part isn't believing in dust. It's catching it fast enough and across enough colors that you don't mistake its magic trick for a new law of nature. At some point, you have to stop arguing with the light curve and ask the obvious whodunit. Who is the star? That's the detective work nobody brags about, because it's less fireworks and more bookkeeping. You go spelunking through old images of the galaxy from before the bang. You mark the exact spot where the supernova popped, and you squint at anything that looks like a bloated pixel. The holy grail is catching the culprit in pre-explosion frames, so you can say, there, that red blob meet the deceased. Most of the time you're dealing with crumbs, a couple of grainy shots in broad filters, maybe a lucky high-resolution image if someone pointed a sharp-eyed telescope that way years ago. It's like trying to ID a celebrity from a childhood yearbook photo where half the class blinked. Here the neighborhood didn't make it easy. The host galaxy is busy star-forming knots, patchy dust lanes, background glitter. You plant a precise astrometric grid, tie the before and after images together so the supernova's pixel sits on the older frames within a hair's breadth. And then you ask, what sat here before? The answer looks a lot like the usual suspect, a puffed up, cool, red object with the kind of color you get from a red supergiant. Not a clean portrait, but the tint and brightness point to a star big enough to die young and dramatically. Not one of those compact blue speedsters that blow their tops with narrow helium signatures. No exotic tattoos, just the classic bar brawler you'd expect to see leaving at closing time. If you translate that brightness into a mass carefully, because dust likes to lie, you land in the 10 to 15 solar mass ballpark. Give or take a couple, because the last year of a star's life is chaos and dust acts like stage makeup. That number fits the red supergiant problem we've been chewing on for a decade. We see lots of these midweights explode as garden variety Type 2 events, but we hardly ever catch the truly hefty red supergiants, say 18 to 25 solar masses, in the act of dying. Do the big ones collapse straight to black holes and whisper instead of shout? Do their last breaths wrap them in so much dust they show up dimmer and we miscount them? Either way, this one doesn't poke the wound. It slides neatly into the mass range that likes to go boom in public. Now, before we put a toe tag on single red supergiant and call it done, you should know that massive stars are terrible at living alone. Binaries are the rule, not the exception. That matters because a companion can siphon mass, stir the envelope, and generally push a perfectly fine star into a midlife crisis. If there was a partner here, the telltale will show up later. After the supernova fades and the glare drops, a lingering blue point source that didn't exist before, or that existed, but was hidden under the primary's floodlights. People play Where's Waldo? With deep post-explosion images. If Waldo is there, you've got a two-body story mass transfer, envelope puffing, maybe those weird last-minute shells we mapped back in time. If Waldo isn't there, you can still have a binary, just one faint enough to hide. The universe loves plausible deniability. What about the star's chemistry? You can't run a blood test, but you can read the neighborhood. The patch of the galaxy this thing lived in isn't metal poor Tahiti. It's more like a normal suburban block with enough heavy elements to dust your wind with metals. Metallicity, astronomy's word for anything heavier than helium, greases the wheels on stellar winds. More metal, stronger winds. Stronger winds, more mass loss before death. That sets the table for the dance we saw. A gentle, steady wind laying down background fluff for years, spiced up by burps that throw out denser shells. It doesn't force the story, but it makes it easy to believe. You don't need a freak environment to get the veil and the shells. You just need a star in a normal, busy part of town that got spicy near the end. One of the neat party tricks with a pre-explosion identification is watching it disappear. If the bright red source you flagged is really the progenitor and not some cluster of smaller stars, it should be gone when you come back a couple of years later and the supernova's faded. That's a morbid, beautiful check. In a handful of well-studied cases, the before source vanishes and you can sign the certificate with a flourish. We'll need patience here. The late-time dust and that stubborn engine heating we argued for keep the scene glowing longer, so you wait for the embers to cool and then take the roll call. If the red blob is missing, case closed. If it's still there, the old light was a cluster or a blend, and we were reading the tea leaves in a muddy cup. Neither outcome is embarrassing. You just update the family tree. Speaking of family trees, the spectrum gave little hints about the star's upbringing. The nitrogen lines, those fleeting early flash, features tend to get stronger if the star dredged up processed material from inside before it died. That's late-life convection and mixing, the kind you expect in a red supergiant that's been simmering for millions of years. Our flash lines weren't a neon billboard, but they weren't absent either, which fits a picture where the surface had already tasted some of the core's cooking. It's not a smoking nun. It's a greasy fingerprint on the fridge. Every time someone hears magnetar in a supernova talk, they imagine a millisecond pulsar lighting up the room like a rave. Dial it down. If a newborn neutron star sat at the center here, we're going to know only indirectly for a long time. The core is wrapped in expanding schmutz. Any radio pulsations would have to tunnel through a soup of ions and dust, and they won't. What we can do is look for the kind of gentle, persistent reheating that a spinning down neutron star provides, and check if the late-time spectrum starts to look more like an inner nebula than a cooling ash pile. The hints we have tilt that way, but don't demand it. A fallback drizzle material raining back in and paying out heat by gravity can fake a modest engine pretty well. If the pre-explosion star was on the lighter end of our mass range, a neutron star is the default remnant. If it edged heavier and shed less than we think, a black hole is on the table. You won't see either directly now. You'll read their signatures in how the wreckage warms, cools, and glows in lines you can't get from nickel alone. There's one more unglamorous but powerful clue: motion. If you take spectrum months apart and measure the spacing of those big hydrogen features, you see the expansion speed dialed down, but not as fast as the clean textbooks say. We already blame dust for hiding the slow inner stuff, but there's a progenitor angle too. A fluffier star one that had lost some of its outer mass before the end puts less inertia in the way of the shock. So the blast coasts a little longer before really biting into denser layers. That again points to a star that had been trimmed, either by its own wind or by a companion. The supernova is the punchline to years of foreshadowing we only spotted after it shouted. If you wanted the romantic version, imagine a red supergiant in a messy relationship. It spends its last few years dropping weight, throws a dramatic tantrum or two in the final seasons enough to fling out a gauzy scarf of gas and dust close to its surface, and a couple of chunkier rings farther out than its core gives way. The shock slaps the scarf. Hello, UV flash, sails on, hits the rings on schedule, those mid-time bumps, all while the newborn compact object quietly pays a heating bill from the center, and the wreckage starts, knitting dust that tints the light and hides the slow stuff. We didn't catch a soap opera. We caught the last episodes of a long-running show. Do we know for sure there was a companion? Not yet. Do we know the exact mass to a decimal? No, and nobody honest pretends otherwise when dust is in the mix. But the stack of circumstantial evidence piles up in a way that would make a courtroom nod along. The color and brightness before the bang match a red supergiant in the mid-mass club. The early flash speaks to fresh, close material. The host environment encourages winds beefy enough to set the table. The late-time behavior doesn't demand a monster engine, just a modest one, or a steady fallback drip in a clumsy room. Nothing about that needs a unicorn. There's a quiet satisfaction in that. Shouldn't exist was really shouldn't look like that if you ignore the messy parts. We stopped ignoring them. We dug up the yearbook photo. We read the neighborhood. We listened to the friends. And the story turned into a very human one by cosmic standards. A big star aging badly, making a mess, and going out with character. If we can pin down the disappearance of the progenitor in a couple of years, and maybe spot or rule out a surviving partner, we'll put the last tax on the map. For now, the silhouette is plenty. Time to open the cash register and count the money. Where did the light come from? And did the numbers add up? Supernova people have a party trick called the nickel trick. Not the coin nickel 56, a radioactive isotope that decays into cobalt 56 and then iron 56, dribbling out energy as gamma rays and positrons. For a lot of normal explosions, the peak brightness is basically the day's takings from that decay heat. Translate peak light into nickel mass, and you get a decent first estimate. Do it here, and depending on how much dust you assume in front of the galaxy and how generous you are with distance, you land in the ballpark of a few hundredths to maybe a tenth of a solar mass of nickel. That's respectable for a red supergiant death, not some record-smashing gold rush. The hitch is that the early light was clearly juiced by shock energy hitting nearby gas, which means the nickel calculator overestimates if you pretend the ejecta did everything alone. It's like judging a band by the crowd noise when the warm-up act was a drummer soloing on trash cans. Slide forward a couple of months and cobalt 56 takes over the till. If all the gamma rays get trapped in the expanding rubble, the total light should drop at a very particular pace, about 1 magnitude per 100 days in astronomer speak. That's the cobalt handrail. Ours didn't hold the rail perfectly. It faded slower in some bands, faster in others. And in the infrared, it barely wanted to go down at all for a while. Before you break glass and hit new physics, remember the dust chapter. Grains soak up blue and spit out red. If you only watch the blue, you think the thing is dying too fast. If you add the red, the total energy looks closer to what cobalt can supply. When we stitch the colors into a bolometric curve, the closest thing to counting every photon, we got something that sagged less than pure cobalt for a stretch, then drifted toward the expected pace once the geometry opened up and the gamma rays started leaking out. One theorist, eyebrows in permanent arch, shrugged. Nickel pays the rent. Shocks tipped in for the first month. Dust picked the lighting. Could a newborn engine be helping? That's the magnetar question, the idea that a fresh, Rapidly spinning neutron star with a strong magnetic field leaks rotational energy back into the ejecta like a slow, steady battery. You don't need a comic book engine here. A modest one does the trick. Initial spin of a few milliseconds, field strength that's strong but not absurd, and you get an extra few YY to YY ergs over many months. Translate that into bar language. It's an under-the-table tab the main bill doesn't cover. The look-fors are subtle. A magnetar pipeline tends to flatten the late-time light curve a bit and keep certain inner, forbidden lines bright. Those are ghostly emission features from atoms, like oxygen and calcium, that shine only when the gas is thin and the collisions are rare. We saw those lines hang around, and not just the usual suspects. Oxygen stuck its head up more than once, hinting the core wasn't asleep. That supports a modest engine story. It doesn't force it. There's a perfectly decent imposter, fallback, where some of the ejected material rains back down onto the compact remnant and turns gravitational energy into heat. Fallback doesn't care about magnetic fields. It cares about how much mass the shock barely unbound. In both cases, the signature is a gentle hand under the light curve, not a floodlight. Energy in the bang itself, the kinetic punch, looks normal by supernova standards, of order a few YA ergs. You read that from the line widths, how fast the debris is flying, and from how long the photosphere, the visible surface, keeps up the act before the show goes transparent. If this were a hypernova, a rare over-caffeinated class, the numbers would be larger and the spectra louder. They're not. The shouldn't exist vibe never came from ridiculous speed or impossible energy. It came from the juggling act. Too blue too early without the radio roar. Late light that wouldn't follow the neat cobalt script. Line profiles leaning blue as if someone dimmed the back half, and a tail that refused to die on schedule. The ledger balances once you add 3 entries. A close thin veil of gas for the shock to slap. Dust that grows where and when it wants. And a small, steady heater at the core, or if you prefer, a trickle of material falling back in. None of those are exotic. All of them are annoying if you hoped for clean math. There's a quiet diagnostic that ties nickel, engine, and progenitor together. The strength of the OI doublet at 6,364ths. Y relative to K2, near 7,300Y in late spectra. Oxygen loves a big core. Calcium has a habit of looking strong when densities are higher or mixing shuffled things around. Strong oxygen usually points to a heavier birth mass. Here the oxygen was there, but not shouting down calcium, which fits a mid-mass red supergiant instead of a bruiser. That's good news for the nickel math too. Mid-mass stars tend not to mint absurd nickel yields. We didn't need them anyway. The early shock, tip, and later dust reprocessing kept the books tidy without raiding the vault. What about gamma-ray escape? As the debris thins, gamma rays from cobalt can shoot straight out instead of depositing their energy, and the light curve drops faster than the cobalt handrail. We saw the shoulders of that effect set in around the time you'd expect hundreds of days, not tens again, reminding you that dust tricked the eye earlier rather than nuclear physics changing the rules. A colleague put it in a single sentence that belongs on a coaster: leakage later, laundering earlier. All of this is only as good as your distance and your dimming, and both are unglamorous headaches. Distance comes from the host galaxy's redshift folded through a model of how the universe expands, or, if you're lucky, from a more direct rung, like a known variable star population in the same galaxy. Dimming extinction comes from dust in our galaxy and theirs, and you measure it with colors of nearby stars, or with the depth of tiny interstellar absorption lines. Push the extinction a tenth of a magnitude one way, and your nickel mass swings 20 or 30%. That's why nobody with both eyes open gives you nickel to 3 decimals. We give you a range and the fine print. The fine print here reads: extinction moderate, Distance reasonable, nickel modest, extras required. There's a reflex in cosmology to ask, so can I still use it as a standard candle? The honest answer is you never could use this one without a chaperone. Even the standardizable Type 2 recipes, where you correct for color and expansion, velocity assume the early light isn't juiced by nearby gas, and the late light isn't being laundered into the infrared by dust. We violated both assumptions right in front of everyone. Not a problem if you know it and fit for it. A problem if you're blind to it. The cure is tedious and simple. Start early, stay late, and build the distance on the color and velocity phase where the shock CSM. Fireworks have calmed down and before dust truly muddies the waters. The good news is surveys now catch these things in the first day. The bad news is that means all your neat templates just aged 10 years overnight. Do we need to invoke a pair instability detonation, some exotic electron capture route, or a jet-driven core to get the energy budget? No, pair instability would drown us in nickel and push timescales into the slow epic category. This was spry, brisk, and nickel moderate. Electron capture tends to be dim and fast with different spectral fingerprints. Jet-driven cores advertise with asymmetries you can't miss and often harder high-energy echoes. We got a little polarization, some asymmetry in lines thanks to dust in clumps, and otherwise a star that acted like a star, not a lopsided engine test. If you want a single sentence to carry out of this pub, the light budget balanced once we stopped paying in one currency. Part nickel, part Shoxi SM tip, part IR cashback from dust, with maybe a quiet line of credit from the newborn remnant. That combination also explains why the thing shouldn't exist if you force it into any one box. Every box is wrong by itself. Stack them, and the receipt matches what the detector saw. There's a nice human angle here too. This whole ledger lives or dies on little bits of data most people would scroll past. A few blue points in the first day, a grumpy mid-infrared bump in week 2, a shoulder in the near-eye hour months later, a line that leans left by 30 kilometers per second instead of 20. None of those is a headline. Together, they tell you where the energy came from, where it hid, and who kept paying the bills after the opening night. A veteran summed it up over lukewarm tea. It's never one thing. If it's weird, it's 3 normal things in a trench coat. Let's talk shape. We all draw supernova as perfect spheres because circles are easy and chaos is inconvenient. But the light keeps tapping us on the shoulder saying, hey, I'm not round. The tool that breaks the illusion is polarization, which is just a fancy way of saying the light waves got lined up in a particular direction. If the explosion were a perfectly uniform ball, the scattered light would average out and polarization would be basically 0. Ours wasn't 0. Not headline big, but steady enough and slightly changing with time to tell you the photosphere. The bright surface we see wasn't a smooth beach ball. Picture a dented pumpkin with clumps and folds, maybe a bit squashed along one axis. As one spectropolarimetry die-hard likes to mutter, round stars die messy. The nice thing about polarization is that it's a geometry snitch. Early on, when the atmosphere is thick and opaque, a little asymmetry goes a long way because most light we see is last scattered near the surface. As the gas thins, we peer deeper and the polarization can drift because the shapes of those deeper layers aren't necessarily the same as the outer skin. That drift showed up here, not a spin of the compass, more like a gentle turn, which tells you the inner ejecta weren't aligned carbon copies of the outside. If you're thinking jet, slow down. Jets leave loud footprints, big polarization swings, screaming velocities, hard X-rays, bragging about shocks boring through. What we saw was the quieter story of a lopsided core and clumpy mixing, the kind you get when a star shudders itself apart and plumes rise like hot soup bubbles. Spectra back this up in the most low-tech way imaginable, by leaning. Take a nice fat emission line hydrogen, say, and you expect its bright core to be pretty symmetric if the gas is expanding evenly. Now tilt the playing field. If dust forms on the far side, that far side redshifted light has to tunnel through more crud, so the line gets a little extra blue on the near side. We saw that lean grow as the months ticked by, hand in hand with the infrared glow from grains. It's not a perfect ruler, but the timing and the direction match. Now look at oxygen later on, when the outer hydrogen is thin and the inner plumbing starts to shine. The oxygen lines were broader than the calcium ones and showed small shoulders, like a singer's vibrato. Shoulders mean substructures, clumps, or rings moving at slightly different speeds. That's 3D, written in 1D ink. There's a party trick we like in the nebular phase, nebular meaning late, when the ejecta are thin enough that forbiddance lines appear. Forbiddance just means the atoms are so spread out they can radiate from otherwise shy transitions. Those lines act like interior lights in a haunted house. You can do crude tomography with them. If the oxygen line shows a dip at zero velocity and twin humps on either side, you're looking at a hollowish distribution, like a shell or torus, where the middle is underfilled. If it's a single peak with a beefy blue shoulder, you're probably staring down asymmetry with a dust bias. Ours lean toward the single peak plus shoulder family, rather than a clean double horn ring, which again argues for clumpy blobs over a pristine donut. One colleague summed it up: more meatball sub than bagel. Now, could a weakly collimated flow call it a jetlet? If you like cute words have helped, you can't rule it out. Core collapse simulations love to cough up plumes and sometimes organize them along preferred axes, especially if rotation and magnetic fields are non-zero. But the key is scale. A real jet picks the outer layers hard and leaves a velocity class that doesn't blend quietly into the rest. Our outer speeds were respectable but garden variety, and the polarization never went rock concert. So if there was a jetlet, it was a chef's kiss of asymmetry, not the main cook. There's another geometry fingerprint hiding in the time it takes for different elements to turn on. Hydrogen hogs the early show because it's everywhere in a red supergiant's envelope. Oxygen and magnesium live deeper in layers that used to be the stars inside. If mixing is strong, you dredge oxygen outward and see its lines earlier and broader. If mixing is timid, oxygen waits for the hydrogen to thin. We saw oxygen come up to the mic on a reasonable schedule and with shoulders that said, "I've been stirred, but not pureed." That plays nicely with the mid-mass progenitor we fingered and the modest engine we debated. Enough oomph to shuffle the deck, not enough to flip the table. Asymmetry also answers a nagging question about the early flash and its pet radio silence. If the pre-explosion material around the star of the circumstellar medium, or CSM, was clumpy and not a nice smooth shell, then the shock could slam into a dense knot in one direction and make a bright, short-lived UV optical burst without having to produce a global, long-lived radio display. Radio wants large-scale, sustained electron acceleration in low-density magnetized zones. If the dense stuff is patchy and mostly off our line of sight, the radio can be shy, while the light we see still gets a wallop from a localized faceplant. Viewing angle is the oldest magician's trick in the book, and we fall for it if we assume the fireworks look identical from every seat. A word on viewing angle. If you tilt the wreckage relative to us, the polarization sees a different cross-section. The dust hides a different fraction of the far side, and the line profiles skew differently. Two observers at 90 degrees could write two subtly different papers about the same supernova. That's not hand-waving. It's a built-in selection effect. We got the seat where the dust didn't totally murder the red wing, but did enough to lean it, where the early UV flash had a clean shot, and where the inner asymmetries turned into small but readable tweaks in polarization angle. Change seats, and maybe you'd call the same event more normal or more weird. I'm fond of the grizzled comment from a senior spectroscopist: half of controversy is just bad seating. Geometry even slips into the color story. If the photosphere is oblate squashed, its temperature distribution isn't uniform. Different latitudes contribute differently as the ejecta expand, so the color evolution can look a hair too blue or too red at certain times compared to a spherical model. Stack that with dust re-radiating in the infrared, and you can mimic a composite of temperatures without changing the physics of the heat sources. That's why we kept saying you have to count all the photons blue, red, and invisible mid-infrared before you accuse nickel or a magnetar of misbehaving. The shape is arranging the light on the plate. There's a fun side alley. If clumps are real, they shadow and self-shield. A clump cooled by radiation can condense dust faster than its surroundings, which then makes it a better radiator, which cools it more, a positive feedback loop. That gives you patchy dust formation, exactly what the polarization drift and the line leans imply. It's the same playbook as clouds on Earth. Once you see the cool patch, condensation snowballs. Then, once the reverse shock sweeps back in months later, it crushes some clumps, heats them, and you get those wiggles in the infrared light. Nothing mystical there. It's just weather in a star's ashes. One question that always comes up in the Q&A is whether we can map this thing in 3D for real, not just vibe about it. The honest answer is we get a paper-match model, not a CT scan. But between polarization angles marching slowly over time, line profiles growing shoulders, and the staggered arrival of different elements, you can assemble a convincing diorama. Outer hydrogen still a bit bumpy, inner oxygen and calcium sitting in mottled blobs, dust knitting first in the densest pockets, a mild axis you could point to, but not swear under oath. A postdoc put it better, an unmade bed, not a tornado. And that's enough to decide whether you need exotic engines. You don't. Messy hydrodynamics carries the day. If you're thinking about the remnant, what's left at the center geometry whispers there too. A neutron star with a kit could be rocketing off at a few hundred kilometers per second, dragging its little magnetosphere through the debris. You won't see the object yet, but you might see slight asymmetries in the inner forbiddance lines strengthen in the same direction over time as the ionization cavity wanders. We didn't get that drama. The inner glow's asymmetries were modest and mostly trackable by dust and clumps. That leaves the remnant's personality an open file, which is fine. The late-time radio and X-ray scene in the next couple of years will have a better shot at blowing the whistle if a pulsar wind nebula lights up. So, no perfect sphere, a dented, layered, clumpy blast seen from an angle, with dust doing its favorite misdirection act and a central heater, if present, playing quietly. That geometry pulls the rug out from under the shouldn't exist headline. It should exist. It should look quirky. The only thing that shouldn't exist is our expectation that a dying star owes us symmetry. A colleague once raised a glass and said, "Spherical cows make bad steaks." Stars aren't cows, but you get the point. So what now? Do we pack up the telescopes and go home? Not even close. The early fireworks told us who threw the first punch, but the long game is where you catch the whispers from the wreckage. Think of it like a stackout after the heist. The main blast was the smash and grab. Now we sit across the street with coffee and watch who keeps the lights on at 3 a.m. First, radio. I know we groused that the early radio was a no-show, which killed the hyperactive shock storyline up front. But radio is patient. As the shock plows outward into thinner, magnetized gas, it can start accelerating electrons efficiently, and those electrons glow in radio bands. If there's a broad, low-density cocoon beyond the clumpy inner stuff, the signal can drift up months to a year later, rising around a few gigahertz and peaking at, say, tens to hundreds of microjanskis if the energy and density are modest. Translate the bar talk. If a late radio hump appears, we can measure how much of the circumstellar medium is out there and how fast the shock is chewing through it. No hump? Then the dense stuff really was local, just scarves and rings, and beyond that, it's a skinny halo, which fits the quiet neighborhood we painted. X-rays are the other pair of stack-out binoculars. Hot shocks make X-rays the way a frying pan makes sizzle. Early on they were tame, which matched the absent radio. But when the reverse shock, the one that travels backward into the ejecta, wakes up, it can heat clumps to tens of millions of degrees, and you get soft X-rays in the 0.3 to 2 keV range. If those X-rays bump up while the optical settles, that's the reverse shock punching into the dense knots we already smelled in the spectra. If the X-rays stay flat, but the infrared swells, dust is stealing the show instead. One high-energy friend of mine likes to shrug and say, X-rays don't lie, they just arrive late. Speaking of infrared, this is where we pass the hat. Dust doesn't just change the color, it changes the physics ledger. Hot, fresh grains glow like a space heater, peaking at a few microns when they're new and toasty. Think 1200 to 1500 K in the first months, then sliding to cooler temperatures, a few hundred Kelvin, as they radiate away energy and move to the mid-infrared. If you watch that glow at multiple wavelengths, you can actually estimate a dust mass. Not perfectly grain size and composition are slippery, but you can say, we've got of order 10 to 4 to 10 minus 2 solar masses of dust, and be honest about the error bars. That matters because there's a bigger argument humming in the background. Who made all the dust we see in the early universe? If ordinary core collapse supernova like this can pump out serious dust and not have it all shredded later, they're part of the answer. If the dust turns out anemic, we have to lean harder on other factories. There's a deliciously awkward trick we can try once the glare really drops. Go hunting for the survivor. If the progenitor had a companion bright enough to see, and if it didn't get obliterated or buried in the ejecta, it might reappear as the supernova fades. In practice, you come back with sharp images 1, 2, 3 years on, and compare to the pre-explosion frames. If the spot where the red supergiant used to be is now dark, and a faint blue speck sits off to the side by a few hundredths of an arcsecon, that's your partner peeking through. If nothing returns, that doesn't kill the binary idea. The companion might be faint or dust smothered, but a detection would be a mic drop. Someone in the back of the room always asks, could the companion have been the one that made those last-minute shells? Entirely possible. Mass transfer is messy. It doesn't just slim down the primary. It can fling out gas in weird geometries that explain those timed bumps we saw. Deep in the ashes, the compact remnant is either a newborn neutron star or a baby black hole. We won't see the object directly yet, but we can eavesdrop. A neutron star that's spinning fast with a decent magnetic field leaks energy like a tiny dynamo, and over hundreds of days, that steady drip keeps certain inner emission lines brighter than radionuclide heating would predict. If a faint pulsar wind nebula turns on, you might catch a subtle hardening in X-rays or a change in line ratios deeper than calcium and oxygen, the spectroscopic equivalent of a distant engine rev. If instead the light curve quietly tilts down once gamma rays from cobalt start escaping, fallback is the likelier heat source. A slow rain of ejecta back onto the remnant, converting gravity into heat. No billboards either way, just the glow of the room long after the party. There's another follow-up that sounds dull and is pure gold. Keep taking spectra long after everyone else loses interest. When the ejecta thin to the point that forbiddens lines, dominate those delicate transitions that only happen in low-density gas, you can do armchair tomography. Watch how the AOI 6,364 Y doublet changes shape. How Cju near 7,300 Y grows or fades, whether Phi2 lines hang on. Those are the pressure gauges and thermometers of the wreckage. If oxygen dominates and spreads to higher velocities over time, the mixing was strong. If calcium wins and stays narrow, the core got less stirred. We already saw shoulders and leans that argued for clumps. Months from now, those same lines will tell us how those clumps cool, and whether the dust cocoon is patchy or uniform. A nebular phase junkie once told me, late spectra are gossip columns. Everyone eventually says who they sat next to. On the photometry side, just measuring brightness in different colors. The job is to build a bolometric light curve that counts as much of the energy as we can, from blue through near infrared, and, if we're lucky, mid-infrared. That curve is how you separate nickel decay from engine drip from dust cashback. Early on we argued that single-band light curves lie. This is the antidote. Expect the total light to track cobalt decay more closely after a couple of 100 days as gamma-ray escape kicks in. If it doesn't, we've either got a central heater that's more generous than we thought, or a stash of dust quietly re-emitting energy we didn't count. Either way, it's data, not a crisis. Could we get neutrinos or gravitational waves out of this one? No, not retroactively. Neutrinos blow through everything and arrive for only a few seconds at the instant of core collapse. And detectors need the supernova, basically in our backyard within the Milky Way, or its closest neighbors to hear them. Gravitational waves from a garden-variety core collapse at this distance are beneath our sensitivity. That's fine. We've got plenty on our plate. Radio, X-ray, optical, and infrared together are already 4 witnesses on the stand. There's a practical calibration angle too. The standardizable candle tricks people use to get distances from Type 2 supernova assume. The early light isn't juiced by a nearby veil, and the late light isn't being laundered into the infrared by dust. We broke both assumptions. That doesn't make the event useless. It makes it a training video. If you catch the early UV flash, you tag the shock CSN tip and exclude those days from the distance fit. If you measure mid-infrared later, you can add back the dust reprocessed energy and keep the nickel math honest. It's not glamorous, but it's how you stop weird ones from sabotaging your Hubble constant spreadsheets. I'll say the quiet part out loud. What we're really doing over the next 2 years is stress testing our story. If late radio hums, X-rays perk modestly, infrared grows and shifts cooler, oxygen lines keep a little extra swagger, and the total light curve slides toward cobalt once leaks start. A 3 normal things in a trench coat model is the house favorite. If instead radio explodes, X-rays go hard, lines split like tuning forks, and the light curve flattens like a tabletop. Then we'll go back to the menu and circle engine with attitude. Either way, no capes, no magic. Just physics owning up to its messy side. My favorite part? The mundane miracle of repetition. We'll see another one of these different galaxy. Slightly different pace, and the pattern will start to look familiar. A star that aged badly, set its own tripwires, and then obliged us with a bang that looked wrong, only because we wanted symmetry and silence. As one observer grinned after a 3A meter infrared run, we keep expecting opera. The universe gives us jazz. All right, let's zoom out and put this oddball back in the family album. Astronomers love drawers with labels. Type 2, Type 2P, Type EN, because neat labels keep your desk sane. A Type 2 just means you see hydrogen in the spectrum. The P stands for a plateau, that flattish spell in brightness early on. IN adds an N for narrow, because you see skinny lines from slow-moving gas when the blast slams nearby material. Ours? It kept hopping drawers. The early flash and little color hiccups screamed. They're circumstellar stuff. That's gas shed by the star in its last years, so you'd expect loud. IN, signatures and long-lived radio and X-ray chatter. Didn't happen. The mid-game light roughly behaved like a plateau, but with dust playing DJ and remixing the colors. Late on, the inner layers spoke up oxygen, calcium, iron as if a textbook Type 2 were finally clearing its throat. The best description is boring, and exactly right. A mostly normal red supergiant death with a messy porch. Why does that matter? because it says more about the star's last months than it does about the explosion itself. Red supergiants, the bloated, cool, very bright stars that die this way, are leaky. Some just dribble wind at a few kilometers per second for 100,000 years. Some cough proper shells in the final years. A few fling a scarf of gas in the very last months. Our event looks like the scarf model. A thin veil close in, not a thick fog stretching to the next county. That's why the shock could smack into something early and make light without committing to years of radio noise. One theorist I know describes it with a shrug. It sneezed, then died. This is quietly important for the cosmic census. If little last-minute sneezes are common, surveys that catch supernova on day 1 will keep seeing brief blue flashes, tiny UV spikes, and one-night weirdness that vanish if you start watching on day 3. It also means a lot of the surprises from the past were just us arriving late to the party. The physics didn't change. Our timing did. The practical fix is simple and annoying. Watch sooner and watch in more colors, including the invisible ones like near and mid-infrared, where dust tells its side of the story. There's another bookshelf this event nudges: how we use Type 2 supernova as yardsticks. People build distance tricks that rely on the plateau phase and the speed of the ejecta, assuming the early light isn't juiced by nearby gas, and the late light isn't being laundered into the infrared by dust. We violated both assumptions in a single go. That doesn't make the method bad. It adds a checklist. Tag the early shock flash and drop those days from the fit. Add mid-infrared light when dust turns on, so you count the energy that moved rather than vanished. You keep the distance honest. A colleague put it in coffee shop English. It's still a ruler, just don't measure with the dents. Metal making the unsexy, crucial part gets a nudge too. Core collapse supernova like this are the galaxy's recycling trucks, spreading elements forged in the star's belly. The relative strength of oxygen versus calcium later on told us the core wasn't tiny. That means a decent oxygen haul, the stuff that ends up in rocks, lungs, and most things you care about. Nickel-56, the isotope that powers the glow by decaying to cobalt and iron, came out in modest amounts, not a bonfire. That's right where mid-mass red supergiants tend to land. And it's good news if you're tallying how the Milky Way got its oxygen. You don't need exotic monsters to fill the budget. You need lots of these workaday deaths. Dust is the hard one. Cosmic dust sounds like glitter. It's more like grit-tiny solids of carbon, silicates, and such that seed planets and protect molecules in space. We caught dust forming early because the spectrum leaned blue where the far side got hidden, and the infrared quietly swelled. The hot-grained phase temperatures of order 1200 to 1500 K gives way to cooler dust in the hundreds of Kelvin as months go by. If those grains survive the reverse shock that will sweep back in later, they become part of the long-term inventory. If they get shredded, they're a flash in the pan. Our event checks the first box, made some, and punts on the second. Will they live? That is exactly why the long stack-out matters. The early universe seems full of dust sooner than you'd expect. Whether ordinary supernova are good enough factories has been an open argument. This one won't end the debate, but it puts a thumb on the scale marked, "Supernova help more than we thought if their dust doesn't all get sandblasted." Back to the shouldn't exist headline. The only thing that doesn't exist here is the fantasy that stars die symmetrically and politely. We saw asymmetry and polarization, clumps and line shapes, dust patchiness, and a viewing angle that made the far side look different than the near. None of that is a curveball. It's turbulence being itself. Simulations of core collapse without any exotic engines already grow mushroom plume. Instabilities that stir inner layers into outer ones. Add rotation that's not quite zero and magnetic fields that aren't perfectly innocent, and you get a little preferred axis, not a comic book jet. That's the geometry we read. Or, as a spectropolarimetry lifer likes to say with a grin, Round is a lie we tell first-year students. I can hear the question that always arrives next. Did we make a neutron star or a black hole? The honest answer is, we don't know yet. The explosion energy and nickel yield land in the neutron star-friendly zone. The late light didn't demand a roaring engine. A gentle drip either, a modest magnetar spin down, or fallback of material could explain the extra warmth. If a pulsar wind nebula turns on later in X-rays, or the inner forbidden lines of oxygen and iron get suspiciously perky, we'll nudge our guess toward neutron star. If everything fades like cobalt-56 losing its steam and the lines just cool, we'll let quiet remnant sit on the chalkboard. It's not fence sitting. It's letting the wreckage speak at its own pace. There's also a people story lurking under the data squiggles. This case is a reminder that multi-wavelength is not a press release buzzword. It's the difference between a mystery and a shrug. Miss the UV flash, and you get baffled by the early blue. Ignore the infrared, and you accuse nickel of ghosting you. Skip radio and X-rays, and you guess wrong about the shock's neighborhood. The way out isn't a hero telescope. It's the boring heroics of coordination. From backyard class optics that catch night one, to big dishes and space cameras that mop up the parts our eyes can't see. A veteran summed it up at 2 a.m. Deadpan. Team sport. Bring snacks. What does this tell us about how often stars pull the same trick? If you lined up 100 red supergiant deaths, a good chunk will show some kind of last-minute mass loss. A smaller fraction will build enough dust early to tweak the colors, and a handful will do both while keeping radio quiet because the dense bits are patchy. That distribution matters for survey design. It says you want a fast trigger in the blue and UV for the first couple of nights, then a handoff to infrared for weeks, with radio and X-ray popping in for check-ins. It sounds like overkill until you realize we built our tidy supernova categories by watching the middle and guessing about the ends. The ends are where the personality lives. If you're the cosmology type, there's a bean counter payoff too. The better we flag and model these three normal things at once explosions, the less they contaminate your distance ladders. You don't have to throw them out. You tag the early interaction, correct the late dust, and use the clean middle like everyone else. It's janitorial work, not genius, but that's how you keep percent-level measurements from drifting. Someone scrawled it on a whiteboard during a heated Hubble constant debate. Weird does not equal worthless. And because we can't leave without one more simple picture, here's the bumper sticker I'd put on this whole saga. The star lived messy, died normal, and we arrived early enough to see the mess. This shouldn't exist bit evaporates once you stop insisting on a single drawer label. Put thin nearby gas, clumpy ejecta, and fresh dust in the same sentence, and it looks exactly like what we saw. No new forces, no secret particles, no magic engines required. Just a dented pumpkin thrown at space, and a lot of photons telling the truth from different corners of the spectrum. If this whole saga felt like showing up late to a movie and spending 2 hours reverse engineering the plot from the credits, here's the fix. Catch the next one before the opening line. You can't stop a star from glowing, but you can stalk it properly. Red supergiants, the puffy, sunset-colored parents of these explosions, aren't quiet in their final months. They flicker, bloat a little, cough a lot. That cough is mass loss. And when a star coughs, it changes color and brightness in ways even a modest telescope can see if you're paying attention. The game's to treat nearby red supergiants like VIPs at a club. Wristband them, keep a bouncer at the door, and ping the whole street the second they look wobbly. There's a pre-game we almost never do because it sounds boring. Take regular, honest pictures of the same patch of sky over and over. Same filters, same cadence, same stubbornness. When you do that, you catch those last-minute sprints, little brightening runs, tiny dips, mild color swings that smell like a star piling gas into a thin scarf around itself. If you see that scarf go up, you know the shock from the eventual blast will have something to slap early on. The flash that shouldn't exist suddenly becomes a promised cameo. And the neat part is, you don't need a space observatory for that heads up. A network of quick, small eyes can do the night-to-night check, then hand the baton to the big guns when it matters. Kickoff is the hard part, because the universe doesn't send calendar invites. The early signal is blue, brief, and rude. Miss a night, and you lose the best clue about the stuff right next to the star. So you automate the pounce. The moment a pipeline sees a point of light that wasn't there yesterday and looks too blue for comfort, you light up phones. You don't argue in Slack about whether it's interesting. You grab a spectrum, any spectrum, to see if hydrogen is in the room, and if the lines are broad enough to scream, real supernova, rather than an imposter star hiccup. If it passes the sniff test, you swing ultraviolet on it fast, and you don't let go for a few days. That's the window where the shock talks loudest, and the nearby gas gives away its distance and thickness. And you keep breathing in rhythm. Optical for the plateau, because that's the slow burn that tells you what the bulk of the ejector are doing. Near infrared, because fresh dust loves to glow just beyond what eyes can see. Mid-infrared, if you can wrangle it, because that's where the rerouted energy hides once grains grow beyond newborn. Radio and X-rays get calendar reminders for later, because they're the honest reporters of shocks plowing through the outskirts. A lot of this sounds like logistics, because it is logistics. Most mysteries in time domain astronomy turn out to be scheduling failures with nice graphics. Can we call the shot before the snap? Sometimes. A star that's really about to go can brighten in the last days or weeks in a way that's just a hair too lively for normal weather. Pair that with a spectrum showing wind-blown gas around it, and your odds go up. If lightning strikes very close to home inside our own galaxy, you get an early warning system of a different kind entirely. Ghost particles that arrive seconds before the light, letting you pivot telescopes while the core is still collapsing. That's a once-in-a-generation moment. But the same mentality applies at larger distances in slower motion. Pre-explosion jitters, odd colors, and a whiff of nearby gas are your heads up. It's not prophecy. It's pattern recognition with receipts. Machine learning gets tossed around like a magic wand here, and sure, the algorithms help, but the trick isn't that a neural net is smarter than you. It's that it never sleeps and never gets bored by the 1000th normal star that suddenly does something unnormal at 3 a-meter. Let it sort the hay, then make a human call fast. There's an elegance to that division of labor. Computers are good at this looks like those. Humans are good at that's new. Put both in the loop, and the odds of missing the early flash drop dramatically. We can even cheat a little with the past. After the bang, you raid the archives. Was the star there in old images? How bright? How red? Did it twitch in the last year? Did it toss a puff a few months out? That's not post-mortem trivia. That's motive. If you catch a subtle rise 6 months before, you're not guessing about the thin veil of gas anymore. You've seen the star set its own tripwire. Our case had just enough breadcrumbs to make that story believable. Next time, if we behave, we'll have a loaf. The part that will feel like science fiction and is actually just grown-up planning is the fast lane for targets of opportunity. Observatories hate chaos for good reasons. Schedules are built months in advance. But if we want the early UV flash and the honest mid-infrared reglow, we need a handful of emergency brakes we aren't scared to pull. Clear 5% of the calendar ahead of time for events exactly like this, then use it without guilt. That's not romantic. It's policy. And it's the difference between writing a careful paper and writing a shrug. There's also a quiet revolution we can do with people who aren't wearing observatory badges. Citizen astronomers with decent gear and good skies can contribute early color measurements. And those are gold because they tell you if the blue spike is real or just your detector being cheeky. You hand them a 2-filter recipe. They hand you a light curve starting an hour after the alert, and suddenly, your fancy models have a spine. It's not charity work. It's distributed sensing with bragging rights. Now, let's talk about the flip side, because hubris is expensive. Sometimes you will sprint to an alert and discover it's a star burping, not dying. Sometimes you will swear dust has formed because the spectrum leans. And a week later, you'll realize you were fooled by geometry and the far side coming into view. Sometimes the radio will finally sing, and you'll have to admit the neighborhood was denser than you sold on day 2. That's not failure. That's the job. The trick is to bake humility into the plan. Keep watching even when the headline cools. Keep folding in the late bands, and keep a basket labeled, "I might have been wrong," on your desk. The real prize, if we do this right, isn't one perfect autopsy. It's a playbook, not a list of rules. Just the reflexes you want when a bright, blue, new point of light blinks on. Grab a spectrum now. Get UV now. Start infrared now. Schedule radio and X-ray check-ins. Pull the archives. Call the humans. Let the algorithm sift. Don't argue about labels before you've counted the photons. If that sounds like a pep talk, good. We're team sports here. Weird supernovas stop being. Shouldn't exist. Stories the moment you assume the universe will be a little messy, and you plan like you care. And the payoff goes beyond a single oddball. If we can turn these scrambles into muscle memory, we'll start catching stars in the act of laying down their last-minute scarves, measuring how often they do it, and how thick those scarves tend to be. That feeds straight back into the big-picture questions. How much dust supernova really make? How fast galaxies enrich themselves with oxygen and company? How trustworthy our supernova yardsticks are when you stare too closely? The headlines will come and go. The habits we build now are what make the next one feel less like a mystery and more like a conversation with a familiar accent. So yes, this one taught us that shouldn't exist really meant should have watched sooner and wider. Next time we'll do both. And when another dented pumpkin flies apart in some nearby galaxy, we'll already be leaning on the bar, heads up, tabs open, ready to listen from the first pop to the last ember. Here's the moment we push the stool back from the bar, tap the napkin full of scribbles, and say it out loud. The supernova that shouldn't exist is exactly the kind that shows up when a big, tired star lives messy right up to the buzzer. We didn't catch a miracle. We caught bad housekeeping in high definition. A red supergiant, the puffy, cool, sunset-colored kind spent its last months coughing off a thin scarf of gas at a few kilometers per second, left clumps in its own insides like dumplings in soup. And then, when the core finally failed in a fraction of a second, the shock tore out at thousands of kilometers per second, smacked that nearby scarf, and lit up the foyer before the main hall. We arrived early for once, and the universe rewarded punctuality with a weird-looking but perfectly legal light show. The twist in the detective story is that all our suspects are boring. Circumstellar material just the star's own breath, sitting at radii of maybe a few times y2 yp meters. Ejective blast debris racing outward at 5 to 10,000 kilometers per second. Not a cartoon jet, just a lumpy wave. Dust grains of carbon and silicates condensing in pockets that cool to something like 1200 to 1500 Kelvin early on, then dropping to a few hundred Kelvin over months. Put those three in the same room, and you don't get a new physics headline. You get the playlist we heard, a blue-white flash that fades too fast for comfort, a plateau that isn't as flat once dust starts hijacking the energy into the infrared, and late-time spectra, where oxygen, calcium, and iron tell on the geometry by leaning and shouldering instead of being nice and round. An old hand summed it up between sips. Call it 3 normal things in a trench coat. If you want the tidy answer to the guiding question, what do we call a supernova that breaks the rules? We call it a lecture about our rules. We built our labels by watching the middle of the movie at one wavelength. Catch the first 10 minutes in the ultraviolet and the last 20 in the infrared and X-rays, and half the anomalies turn into paperwork. The early ultraviolet spike is the shock hitting that thin veil, not an engine revving to 11. The color drift is fresh dust glowing beyond what your eyes can see, not the radioactive nickel suddenly ghosting you. The polarimetry, the faint fingerprints in polarized light saying the explosion wasn't perfectly round. That's turbulence and a hint of rotation picking a favorite direction, not a secret drill bit chewing through space. As one observer likes to deadpan after a long night, round is for chalkboards. None of this means we've ironed out every wrinkle. We still don't know for this specific blast whether the newborn remnant is a neutron star or a small black hole. The nickel-56 yield was modest, the energy looked garden variety, and the late glow didn't need a hidden engine. That points toward a neutron star, the ultra-dense city-sized ember left when gravity wins, but can't quite crush everything. If months to a year out, a faint pulsar-weaned nebula, think of a baby lighthouse, powered by a magnetic dynamo, starts to whisper in soft X-rays, we'll nod and call it. If the light just slides down the cobalt decay ramp and the inner lines cool like a room after the heater clicks off, we'll shrug and say, quiet remnant. The honest bit is that we're not guessing the ending. We're sitting in the theater until the credits finish. We do know what the blast told us about the life before the bang, and that might be the most important part. Red supergiants don't all wind down like a gentle dimmer switch. A good fraction, judging by surveys that actually look before the fireworks, throw a fit in the last months to years' small brightening runs. Color twitches, hints of denser wind, all signs of mass loss changing gear. A thin shell at a few hundred astronomical units is exactly where a shock moving at a few times 104 kilometers per second would run into it in the first day or two and make a brief ultraviolet flare. We didn't need to invent a new kind of engine. We needed to accept that anxious star's pace before the finale. An uncredited theorist put it with the right amount of salt. It sneezed, then died. There's also a cosmic bookkeeping chapter here. Core collapse supernova like this are the neighborhood composters. The oxygen you breathe, the calcium in your bones, the iron in your blood, they all got their first passport stamps in stars like these, then rode out on debris at thousands of kilometers per second. When we read the late spectra and see oxygen carrying a lot of the weight and calcium doing its share, we're reading the receipts. The numbers aren't pin-sharp line profiles, and luminosities come with uncertainties that are easily tens of percent. But you don't need decimal points to see the trend. Mid-mass red supergiants make plenty of oxygen without turning the galaxy into a junkyard of exotic outliers. That's comforting if you care about how ordinary the recipe for us really is. Dust, the grit that seeds planets and shields fragile molecules, is where the plot thickens. We saw it form early. No question, the blue ward tilt in optical lines from the near side shining through. The extra infrared bleeding in as grains heat up. A quick back-of-the-coaster calculation says you're probably talking about something between a 10,000th and 100th of a solar mass of dust as a first pass, with at least a factor of a few uncertainty, because grain sizes and compositions are slippery little liars. If those grains survive the reverse shock, the inward moving wave that will sandblast the innards as the outer shock plows ahead, they join the long-term inventory. If they don't, they were a beautiful but temporary filter. We won't know until the mid-infrared stays bright while the optical fades. Or it doesn't. Patience is the fee for answers that matter. You might be tempted to ask what any of this does for the precision. Crowd measuring the expansion of the universe with supernova as yardsticks. The short answer is it makes them a little humbler and a lot wiser. Type 2 supernova can be standardized, turned into decent. Distance tools if you know which parts of the light curve to trust. This one teaches the obvious. Don't use the days when the shock is punching a local veil. And don't pretend energy vanished when it actually moved into wavelengths you didn't measure. Flag the early interaction. Add back the infrared when dust turns on. And the plateau phase in the middle still gives you a solid rung on the distance ladder. With uncertainties you can write down instead of hand waving. As a colleague likes to put it with half a grin, it's still a ruler, just don't measure with the dents. What about the scary alternatives? The central engines, the jets, the stuff that makes headlines and sleepless nights. They exist. Some explosions really do get extra oomph from a rapidly spinning, strongly magnetized newborn neutron star, the magnetar idea, and a rare few launch jets that trill their way out and make gamma-ray bursts. This wasn't one of those. The early ultraviolet didn't stay hot, the radio and X-rays didn't roar right away, and the late decline didn't flatten into a telltale engine drip. If you're keeping score, that leaves us with the comfortable middle, turbulence and mild asymmetry in the core, collapse due to the stirring, not a hidden power tool. One veteran's line that stuck with me: engines are for the few. Most stars go out on a budget, so where's the climax? Right here, the mystery collapsed into method. You built a mental model that fits every oddity with the fewest moving parts nearby: thin gas for the opening slap, clumpy ejecta for the crooked line shapes and the polarization, early dust for the color mischief and infrared swell, and garden variety decay for the slow fade once the gamma rays start leaking out. Every piece has units you can put on it: velocities in kilometer per second, temperatures in Kelvin, dust masses in sobering fractions of a sun, with uncertainties you aren't shy about. Every piece has a way to be wrong. Later radio could rise, X-rays could perk, a pulsar might blink, and you've already booked the time to let the universe correct you. That's not a plot twist. That's how you write an ending you don't have to apologize for. The other payoff is cultural. Time domain astronomy, the business of watching the sky change, isn't a soliloquy. It's a chorus. Early blue needs small, fast telescopes with itchy trigger fingers. Infrared needs the heavy lifters. Radio and X-ray need patient ears. Someone has to keep a citizen army of skywatchers caffeinated. Someone has to bully a schedule so a target of opportunity isn't a dirty phrase. The reason this impossible supernova ended up being ordinary in a fancy hat is because the right people stared at the right wavelengths at the right times. There's a kind of blue-collar beauty in that. A grizzled spectroscopist said it best while packing up a frozen laptop at dawn. It's amazing what you can learn when you just don't stop looking. If you're still craving a moral, here's mine, plain and unpoetic. The universe doesn't owe us symmetry. Stars die the way people live, with habits, hiccups, and a little drama at the end. When you see a light curve cough, a spectrum lean, a color drift, don't write a conspiracy. Write a to-do list. Get the UV before the flash fizzles. Get the IR before the dust cools. Peak in radio and X-ray when the shock finally hits the suburbs. Come back months later and read the ash and forbidden's lines, the delicate transitions that only light up in thin gas, and let the oxygen and calcium tell you where the furniture fell. That workflow is the real answer to the headline. Shouldn't exist is just a way of saying, we showed up late, short-handed, and with one eye closed. So, yeah, it exists. It always did. We finally watched enough of it to see why. The scarf of gas was close. The blast was lumpy, the dust was early, and the physics was the same stuff you learn in the first third of the course, just stacked in the right order and played on more than one instrument. Pull any one band out of the orchestra, and the tune sounds strange. Let everyone play, and you get a melody that makes sense. No miracle required. Just attention, patience, and a bar tab's worth of notes. Okay, last round, one more sip, and then we call it. If you walked in tonight thinking a supernova that shouldn't exist meant we'd uncovered a magic trick, the punchline is more human than that. We didn't catch a new law of nature. We caught ourselves showing up earlier, staring longer, and listening in more colors than we used to. That's the real plot twist. A big, puffy red supergiant, the kind of star that looks gentle until it isn't spent its final months shedding a thin scarf of gas. The core caved in faster than a blink. The resulting shockwave punched through the star and slapped that nearby scarf. And for a few hours, the whole thing glowed in a way that looks wrong if you only watch the middle of the movie. Then the show settled into the familiar slow burn, with dust forming like fog in streetlight, and the deeper layers speaking up in their own accents. That's not cosmic heresy. That's a messy ending performed by a pro. The nice surprise is what this does for our eyesight. For years we loved tidy drawers, type this, type that, because categories keep your head from exploding. The universe, being the universe, prefers cluttered countertops. We got comfortable labeling these deaths by how they looked weeks in one band of light, and we quietly ignored the fact that most of the personality lives in the first 48 hours and the last few months. This event smacked that habit out of our hands. Early on, the ultraviolet spike told us there was gas close in. Mid-game, the color drift whispered that dust was stealing energy and rerouting it to wavelengths just beyond what our eyes see. Late on, the quiet glow decayed like a clockwork isotope. And the thin, forbidden lines, those delicate transitions that only light up in sparse gas, let oxygen and calcium testify about the layers. If you listen to all of it, the impossible becomes inevitable. One observer put it bluntly over cold coffee. Nothing broke. We just finally sat through the whole film. What we know, without crossing our hearts or sacrificing any goats, is simple enough to carry in your pocket. The explosion energy landed in the normal neighborhood. The debris, the ejecta, rushed out at a few to 10,000 kilometers per second. Not a comic book jet, just a lumpy wave. The nickel 56 that powers the glow was modest, which is typical for these stars. The early flash needed a little nearby gas, not a secret engine. Dust turned on sooner than our lazy schedules used to notice. The geometry wasn't perfectly round, because nothing in the real world is. What might still be in play is the fate of the core. A neutron star is the neat fit, the city-sized ember that sometimes spins and beams, and sometimes just sits there being absurdly dense. A small black hole is the quiet alternative if the center had a little more mass than the explosion could rescue. Give us months and a few patient X-ray check-ins, and we'll stop hedging. The universe pays on its own calendar. The fun bit, the part that should make you grin on a random Tuesday, is the way this reorders our to-do list. Time domain astronomy, the art of not blinking, used to be a handful of heroic snapshots. Now it's a rhythm section. If the sky throws a new bright point of light at you, and you can hit it with a quick spectrum, you know within minutes whether hydrogen's in the room and how fast the walls are moving. If you can swing the ultraviolet early, you catch the shock talking to that thin veil of gas, and you measure how far out the last cough landed. Keep optical eyes on the plateau, and you watch the bulk of the debris cool. Keep near and mid-infrared ears open, and you hear dust crackle on. Keep radio and X-ray in your back pocket for later, and you'll know when the shock hits the suburbs. That's not poetry. That's groceries. And when we did it on this one, the shape of the truth just walked out and shook our hand. Zoom out from the lab bench, and the story gets softer and bigger. Stars don't go quietly. They go honestly. They live with winds and hiccups and mood swings. Then they fail in a heartbeat and throw their insides at space. That violence is the reason we're here to make speeches about it. The oxygen in your lungs, the calcium in your teeth, the iron that lets your blood grab oxygen and haul it around. None of that existed at the Big Bang. It was assembled inside stars and delivered by events like this. When we tease apart a spectrum 10 months after the blast and see oxygen shouldering the load, we're reading receipts from the factory that built us. One of the grizzled line cooks in this business likes to say, "Dry as toast. Every breath is supernova gossip." He's not wrong. So what did the "shouldn't exist" headline actually buy us? Better habits, for one? We'll be quicker to assume that many red supergiants cough in the last year, laying down just enough material to make an early slap without cluttering their whole neighborhood. We'll be slower to trust a light curve that forgets about the infrared and then acts surprised when energy goes missing. We'll be kinder to polarization measurements that tell us explosions aren't perfectly round, and we'll stop pretending that symmetry is the price of understanding. We'll admit that our yardsticks, turning these plateau light curves into distances, work fine as long as you mark the dents. Skip the juiced first days and add back what the dust stole. None of that is sexy. All of it is how you get from cute story to clean measurement. And yeah, there's romance left. There's the fantasy that next time we'll catch one in our own backyard, and neutrinos, the ghost particles that bullet out of the core before any light escapes, will ping our detectors and text the whole planet. It's happening. There's the daydream that a newborn neutron star will cough a baby pulsar wind and we'll watch a lighthouse spin up inside fresh debris. There's the quiet hope that we'll actually see dust grains survive. They're sandblasting and join the long-term grit that seeds planets. Those are maybes, not guarantees. But that's a good thing. Confidence without curiosity is just a nap. If you've stuck with me this far, you've probably caught the theme. We didn't defy the rulebook. We realized the rulebook was an index to a much longer story. We didn't find a supernova that shouldn't exist. We found one that shouldn't be judged by a single photograph taken in one color on one night. The moral is stubborn and a little old-fashioned. Show up early, stay late, and keep an open tab for the parts of the spectrum you can't see with your eyes. The universe isn't out to confuse you. It's out to be itself, and it will meet you halfway if you do the boring heroic thing and keep watching. So here's the deal. If this Barstool tour made you look up a little longer tonight, hit that subscribe so we can keep doing this without selling my telescope for parts. Drop a comment with something specific so we can argue in good faith down there. If you had one instrument to point at the very first hour of the next impossible supernova, would you grab ultraviolet to catch the shock slap, or infrared to catch the first breath of hot dust? And why? And since you get a vote on where we wander next, pitch the mission. Do we chase a magnetar-powered firework and ask what a newborn, over-caffeinated neutron star really does to its surroundings? Or do we raid the ghost of a famous blast and dissect those eerie rings lighting up decades later? If there's a weirder corner you want to explore kilinovae, starquakes, rogue planets ejected by explosions, say the word. This channel is the kind of ship that sails where the crew points. I'll leave you with the ugliest, truest sentence in this line of work, the one a mentor muttered while fighting a frozen dome at 3 in the morning. It's amazing what the sky will tell you if you just don't stop looking. That's our North Star. We aren't trying to make the universe behave. We're trying to be present enough to hear it when it clears its throat, sneezes, and yes, dies spectacularly, for reasons that make perfect sense when you've earned the right to say you were there from the first pop to the last ember.